கேட்கல. ಇದು there ಅಲ್ಲಿದ್ದು I don't know whether they're okay. Oh, ಎಲ್ಲ
Sir.
Hello.
Hello, sir.
Good morning, sir.
Good morning. I'm ready.
Sure, sir.
I didn't want to be delaying. Okay. How are you, everybody? Nice to see you.
Fine, sir. Fine, sir.
Yes. Good to see you. I'm glad that you're organizing this year.
Yes.
Chidambaram.
Your blessing, sir.
Always pleasure. So everyone is online only.
Sir, we expect two more people, sir. So they
let
will
them
be
join.
shortly available online, sir.
After some time.
Every morning has a new beginning, a new blessing, and a new hope. It's a perfect day because it's God's gift. Wishing you all a Kalai Vanakkam and a blessed and cheerful good morning. With immense zest, the Department of Electronics and Instrumentation Engineering and NPMAS National MEMS Design Center welcomes you all for the inaugural of AICTE Atal-sponsored online faculty development program on MEMS. It's a mark of our undying tradition to begin with invocation. Let's all join for the Tamil Thai Valtu.
அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசை இருந்த பெரும் தமிழனுக்கே தமிழனுக்கே சீரிழமை திறமையென்று செயல்படுத்தி
Thank you. Our desire is to extend a gracious and inclusive welcome to all. May I now request Dr. S. Kavita, Assistant Professor, Department of Electronics and Instrumentation Engineering, and the coordinator of ATL FDP, to welcome the gathering and to present a brief note on the theme of this FDP.
Good morning to everyone. It's my pleasure to welcome you all the AICT Atal sponsored online faculty development program organized by Annamalai University. I welcome Dr. R. Kailveri Madam, Professor and Head, Department of Electronics and Instrumentation Engineering, our beloved Professor Dr. R. Joseph Daniel Sir, Coordinator, NPMAS National MEMS Design Center, and my colleagues and students. I extend my warm welcome to our Chief Guest, Honorable Chief Guest, Professor Dr. K.N. Bhatt, who is a visiting professor, Center for Science and Nanotechnology, Indian Institute of Science, Bangalore. We feel very happy that you have joined us, you have joined with us, and we are really thankful to you, sir, for taking the time out of your busy schedule to attend this function. Thank you, sir. I also extend my warm welcome to all the eminent speakers and participants from all over the country and from different walks of life. You have come here to share your knowledge and vast experience with the research community. Once again, I welcome all. The breathtaking advances in the field of microelectronics over the past 20 years has made the implementations and the electronics realization of real-time fast power electronics, power efficient computer systems, digital signal processing, communication system, biomedical systems, and system for consumer goods reality. So circuit complexions of millions of transistors are now common, and advances in silicon processing and geometry reduction are set to continue for many years to come. So MEMS is a very multidisciplinary field, and it requires the knowledge of electronics design, fabrication technologies, measurement systems, and mechanics. To reflect these requirements, this program to study includes the microelectronics device fabrication and design modules, as well as specialized options on microsystem technology. So to be able to take the advantage of these advances in microelectronics and sensor technology, this will always be a need for suitably qualified engineers with the experience and know how of the latest technologies developments and support tools support them. So this can be achieved only by first educating the teachers and industrialists involved in VLSI design and technology, so that they in turn teach their students in their institutions. So this staff development program aims to give the faculty and technologists from various industries and skills and knowledge to make it worthy contribution in the VLSI, microelectronics and MEMS industry. But the outlook remains optimistic despite the problems in the world economy. So with this background, we have invited 14 resource persons from renowned institutions who are all currently working in the recent trends on MEMS. This program serves to act as a bridge on to enrich the knowledge on MEMS and nano devices, fabrication techniques, microfluidics, and hands-on trainings on MEMS tools, etc. So this program could help burden the faculties and the researchers to have an interaction with the pioneers in the field. I request all the participants from across the country to make use of these 5 days to the best of their abilities. I hope all of you enjoy with this faculty development program. Thank you all.
Thank you, ma'am. I feel much elated to call upon Dr. R. Kylbury, Professor and Head, Department of Electronics and Instrumentation Engineering, to deliver the presidential address.
Respected chief guest of this faculty development program on micro electromechanical systems, Professor K.N. Bhatt, visiting professor, Center for Nanoscience and Engineering, Indian Institute of Science, Bangalore, the guest of honor, and I thank him for having accepted to deliver the inaugural address. And my friends, Dr. Joseph Daniel, Dr. Kavita, Dr. Manivallan, my dear colleagues, and my dear participants. A very good morning to one and all. I congratulate Dr. S. Kavita, the coordinator of this FDP on MEMS, for having taken all possible efforts to organize the this FDP. Nowadays, these types of programs have become vital in bringing out the research outputs. Also, this program will enable the participants to establish contact with the lead researchers and pave a way for academic exploration in said areas. MEMS has been identified as one of the most promising technologies for the 21st century and has the potential to revolutionize both industrial and consumer products by combining silicon-based microelectronics with the micro machining technology. If semiconductor microfabrication was seen to be the first micro manufacturing revolution, MEMS is the second revolution. The complexity of MEMS is also shown in the extensive range of markets and applications that incorporate MEMS devices. MEMS can be found in systems ranging across automotive, medical, electronic, communication, and defense applications. This FDP has provided a forum to deliberate on MEMS and its applications. It gives me pleasure to point out that 14 lectures on MEMS have been arranged. It is an unique opportunity for the participants. I strongly hope that the sessions will definitely impart knowledge relating to the field and the participants will be greatly benefited. I wish you all the best. Thank you.
Thank you so much, ma'am. We have come to the phase of lending our ears to the chief guest of today's virtual gathering. It is none other than the renowned Professor Dr. K.N. Bhatt. Professor K.N. Bhatt completed his BSc in Mysore University in 1963, then did his bachelor's degree in engineering in IISc. He completed his master's degree in IIT Madras and RPI Troy, New York, USA. He did his PhD in IIT Madras. Dr. Bhatt was a professor of IIT Madras and is currently a visiting professor at IISc Bangalore. He has also rendered his service as visiting professor in the Electrical Engineering Department, University of Washington, Seattle, USA. He is a fellow of the INAE. He has immensely contributed to the growth of VLSI and MEMS technology, education, and manpower development in India. I feel honored to request our respected chief guest to deliver the inaugural address.
Thank you, madam, for the invitation. In fact, Dr. Kavita said she was surprised when I accepted because, okay, but I wanted to surprise her by accepting. Because he said, please talk. Usually I go for technical talk, that's why she was surprised. But here,
Sir, you are not audible, sir.
oh, I'm not, oh, I didn't put this down. Are you audible now?
Yeah, sir. Now it's okay, sir. Now it's okay.
Oh, didn't put this down actually. So do I start from the beginning from the
Yeah,
Yes. Yeah, I'm thankful to Dr. Kavita for inviting me to be present here. I'm not a great talker for the inauguration and all that because I usually do the technical talks. Okay, but still, I'm very pleased to note that the Annamalai University has done so very well under the leadership uh, of Joseph Daniel, and a lot of work is going on in Chennai and other places in the area of MEMS. When we started the MEMS activity in India, somewhere around 2000, there are hardly few people working on that. In fact, Dr. Joseph Daniel was one of the lucky persons who was present at that time when we started this work. So this MEMS activity was rather new in those days, but gradually it has picked up so much that now every college, every IITs, they have got a topic or a subject for teaching this, and everyone is eager to work in this area because this area is a combination, as the name this tells, MEMS, combination of mechanical engineering, devices which do mechanical activity, and also electrical engineer, and also electronics people. The joy is maximum when all these people, me- mechanical, electrical, electronics, and the whole lot of people in engineering participate in this program. In fact, in IAC, we have a lot of people coming here from various disciplines. For me, it's a joy to meet some of them when they come here and they come and say hello and do some consulting work with me. Consulting free. Okay. I don't charge consulting. So it's actually a pleasure that uh, to come over here to uh, give this inaugural talk. In fact, uh, in fact, Kavita said she was surprised when I accepted. Okay, because she didn't expect I will accept the invitation probably, but I made a point to make sure that I am present for this organization, particularly because he is involved, whom I know very well, and Dr. Daniel is there. Dr. Daniel spent I don't know how many years, about 4 or 5 years with me in IIT Madras, and we had excellent relationship, interacting in the technical thing. In fact, I remember, very fondly remember, him working day and night when he was not well. And I also remember Madam, his wife, accompanying him to come to the lab to make sure that he is safe there. And all these are memories which I carry with my mind. So I don't think I should spend too much of my time. The, all of you know that MEMS is the hottest area now. There is no university which does not have a place for MEMS. And lot of technical things have come up in this area because it is not just proprietary of electronics people. It belongs to everybody. It belongs to mechanical. It belongs to civil engineering people. It belongs to doctors. Okay, you say, how do you say it's for doctors? See, one of the MEMS component that is required, in which I started at beginning in the IAC, is the intracranial pressure sensor. The intracranial pressure sensor, I don't know how many of you understand, many of you will understand, is a sensor which will be inserted into the intracranial position, make a hole in the skull and insert the sensor. Can you imagine that? I have seen this operation taking place in Nimans in when the year sometime uh, 2008 or something like that, when they contacted me that they want a sensor for inserting into the intracranial position. Why is it required? Why should I want to measure monitor the pressure? Normally, we don't want to drill a hole on the head of a person. But if you want to monitor the pressure, you have to access that through by inserting a sensor. Now you can see the job of this sensor. It has to respond to the pressure. It should not disturb the body. That means it should be biocompatible. It should be mechanically strong. See, those are all the requirements required, which is much more than a simple electronic component calls for. So mechanical, electrical, everything is there, electronics. So at that time, in fact, I hope a couple of minutes I can take. When I was called for to demands, not for undergoing operation, but to watch the operation. I saw the operation be taking place. I went with Professor Nokant Bhatt and a couple of other students. Some of them said, I don't want to see the operation, as if it's something big happening. But I saw a small drill is taken and the hole is drilled, and the drilling is over in the fraction of in a minute, and this sensor is inserted. So those people had called me because they wanted me to make a sensor in this area which will be compatible with a low pressure. How much is the pressure inside? Can anybody tell? I did not know until the time. The pressure inside there in the intracranial position, normal pressure is 15 millimeter of mercury. You can see that there is vacuum here. Okay, 15 millimeter of mercury normally. But when there is a road accident, when the fellow falls on the road and gets head injury, the pressure goes up. Pressure goes up. Even during examination time, the pressure goes up. The indication of the pressure is headache. If the if you get headache, the meaning that pressure, intracranial pressure is going up. Okay, so that is the thing that they wanted to make the sensor, and we had made that, but were not able to make it biocompatible at that time. We have at the request now, again toward the end of my career here, I am again working on the thing to bring it to a conclusion so that they have the thing. So that is one of the applications for biomedical applications. Other one is of course catheter, where you can put a catheter into the arm here and monitor the pressure there. If you insert the pressure sensor, the pressure, the sensor will indicate more pressure if there is a block. So you can insert the sensor, see whether the block is there. If the block is there, you should be able to break it right away there. So I think my time has come. As I'm seeing I kept the clock here because I don't want to exceed my time. There's 9:20. But having said that, the MEMS area is not proprietary of electronics people. It's not proprietary of mechanical people. It's not proprietary. It is proprietary of everybody. Anybody who wants to jump into this area can get in. That's how I got into that. In fact, when somebody had come in the year in 2000, asked me to make a pressure sensor, I said, I don't know sensor, I don't know pressure sensor. Then that person told me, I will give a paper to you, you read that, I'm sure you are the person to make it. That's how I get into that. Wishing you all the best. Thank you, Kavita, for inviting me and seeing most of you here on the screen. And particularly thanks to Daniel to show his face here, and he's smiling there, and I'm seeing everybody here. Thank you very much. All the best for the program. Thanks. Okay.
Thank you so much, sir, for delivering the inaugural address, and thank you for your intriguing talk. May I now request Dr. R. Joseph Daniel, Professor, Department of Electronics and Instrumentation Engineering, and Coordinator of NPMAS National MEMS Design Center to offer his felicitation.
I'm not audible actually.
Excuse me, sir. Kindly unmute, sir. Excuse me, sir, you are not audible.
Now I am audible?
Yes, sir.
Okay,
Now it is audible.
okay.
Morning, sir.
Good morning. Good morning, everyone. Uh, Professor Bhatt is there? I am not seeing him in the video. Sir, you are there? Sir, you are there? Professor Bhatt? Sir, I am Daniel. Am I audible to you? Okay, I think. Sir, I am audible to you?
Sir has muted his mic, sir. So
Okay, okay.
but you are audible, sir. You are audible.
Wait.
I am very, very
Okay,
happy.
I'm audible now. Am I audible now? Hello?
Sir, yes, sir.
Okay, okay. I'll mute my.
I am very, very happy to see Professor Bhatt. He has been my guide when I joined my PhD program in 2000. And that was a time I had some, what I can say, I was actually, I applied for a PhD program at QIB. He came forward to support with financial assistance throughout these 5 years. I didn't get any money from the university, but in fact, he fed me and my family. So I am ever thankful to him. I thank God for an opportunity to honor him during this function. In the year of 2000, when I joined my PhD program, of course, I had the fundamental knowledge of electronics, but MEMS was new to me. In those days, only a handful of people were working in the area of MEMS, and Professor K.N. Bhatt was one among them in India. If I say he is the father of MEMS in India, it won't be an exaggeration, because from scratch we started, and when the MEMS pressure sensor was developed at IIT Madras, and the pain he took, and every stage, whenever we cross a milestone, he will be very, very happy. And one fine morning, he rushed to the lab, and I was not knowing, because the previous night they had got some good results. They had it working. So I didn't know that in the morning, and when I came to lab at 8:30, he came to me and, Daniel, you know our pressure sensor is working. So that was a great moment, and that is the first pressure sensor made in India. I mean, I am sure, because after that he packaged the major advantage. The other important thing about that pressure sensor was, see, we integrated the electronics also together. It is not just a Wheatstone bridge; it's a MOSFET amplifier integrated with that. So MEMS, the basic advantage of MEMS is, it is possible, since it is made of silicon, it is possible to integrate electronics with MEMS, and in a single chip we get a sensor with processing electronics. So that was a great milestone achieved in India, and the man behind that was Professor Bhatt. So that is how I also learned about MEMS, and he is a passionate teacher. Semiconductor devices, he is a master, and after I went to IIT Madras, I mean, semiconductor physics, generally people will run away. When you say Fermi level, people will run away. But when after I returned from IIT Madras, now in Annamalai University, semiconductor electronics, everybody can talk about. At least 5, 6, 7 people. They can very easily talk about. So that is how he used to teach semiconductor physics. And even though he was a semiconductor teacher, slowly we are electronics engineers, and slowly MEMS became an attractive thing. So we moved to MEMS, and Professor Kane, but in fact, he had the advantage of working in IIT and then IAC. He is doing extremely very good job, and I can't compare. I used to send our students there for fabrication. He will give every support. He will design. He will in the design of mask and the fabrication. So at least 2 of our PhD scholars, they have fabricated our devices in IIC Bangalore. Especially the Sundari's work. She fabricated a molybdenum beam. I mean, that was the first time a molybdenum cantilever beam was realized. Still, I would say we got some 50% success. Still, there are a lot of things to be done. So he gave a lot of support when I developed the concept of PWM pressure sensor, which will give me a direct digital output. For example, especially in tire pressure monitoring system, where we need to send digital signals for transmission to the dashboard, we need a digital output. So a pressure sensor with digital output. So started from there. He taught me pressure sensors, and now that motivated me to develop other kinds of devices like PWM pressure sensor and other things. In Annamalai University, now so far 10 people have completed their PhD in MEMS area, and in fact, the basic reason is the motivation that I derived from Professor Bhatt. He is now almost 79. Even at this age, he drives the car. He goes to IIC Bangalore, at least 5 to 6 kilometers from his house, and still he will stay there for the whole day discussing with the people. So such a great motivation. So I am talking all these things so that the participants should know that if at all, when you are working as a professional, the dedication that you should show, that is very, very important. That you have to learn from Professor Bhatt. See, he has been a great blessing. And in spite of all these things, a very other important thing that I have seen from him is that he never neglected his family. Even though many times you see people, they will be very busy in their offices and they will neglect the families, and children will not have father's love, and wife will not have husband's love. But you see, since I have close relationship with Professor Bhatt, I know Madam also. See, every evening at 4:30 or 5 o'clock, you can see Professor Bhatt going for a walk with his wife in the campus, and he will spend a lot of time with her. And of course, because of this, and he never neglected the children also. So they are also doing very well. So that is the important thing that you have to learn from him, because most of the professionals, they neglect this part that ruins life of the children and wife. So I am really grateful. He has been, because I have never seen Madam in a sad this thing. Professor, but he has not only contributed in the area of electronics and MEMS. He has contributed a lot to the family and to the society. So he is a complete man, I would say. And uh, I take this opportunity to thank him for all the support he has given me. Of course, I am putting my every nerve to develop certain things in Annamalai University based on his ways, because in 2001, in IIT Madras, we had facilities required for semiconductor processing, but still they were not sufficient to fabricate MEMS. Like, we didn't have bonder and all. But by his great effort, he developed the lab, and that was the first time I remember we called that IIT Madras Electrical Engineering Department. Earlier it was Microelectronics Lab. Now it is Microelectronics and MEMS Lab. Now if I go there, there is tremendous development, because based from the base he formed, the his junior teachers, they have again followed his path and developed a lot of things. And now today we have in IIT Madras more than 200 worth a great lab. But for all those things, the basic seed was sown by Professor K.N. Bhatt. So such a great achiever we have with us today. And I thought he will talk for more time, and he will even give a lecture. So if possible, that is, I request him to give a lecture to the audience, so that people will learn a lot of things from you, sir. And now I the reason that I asked Kavita to invite Professor Bhatt, she asked me first, sir, can you ask? Then I said, you are the coordinator, you have to ask. So she had some doubt. She thought if she sends the mail, probably Professor may not accept. But then I said, you say I am the student of Dr. Joseph Daniel, he will accept. So that is why probably she was surprised. But the moment the word Joseph Daniel is there, I know that Professor Bhatt will say yes. So I never had any doubt. And I am very much thankful to you, sir. And today, Annamalai University has a MEMS design center, and we have introduced a microelectronics and MEMS PG program. We are offering a lot of MEMS subjects, all because of the encouragement that you gave me. And I remember you always tell one statement: the time and money spent on teachers is never a waste. So most of the people, the participants in this program are teachers, I think. See, a lot of time and money is being spent on this for educating the teachers, and I'm sure it is never a waste, because ultimately we the teachers, we transfer the knowledge to the coming generation. So I am very grateful to Professor Bhatt for accepting our invitation and being the chief guest in this program. And as a mark of honor, let us all clap and encourage him. Of course, now next, I have to talk about Dr. Kayalvili, our head of the department. For the past 3 years, she has been guiding our department. She is an able administrator. She has handled complicated situations very easily. And for the past 3 years, she has run the department smoothly. And for the support she has given me and for the MEMS group, it is, I can't describe. Whenever we ask something, whatever I ask, she will help. So we are grateful to you, madam. And I also congratulate Kavita for applying for this program and God being the coordinator. And I welcome Manivannan also, my PhD student and my colleague. So I congratulate every participant who is attending this program, and I am sure a lot of eminent people they have been invited to deliver lectures. So you will all enjoy all the sessions, and you will be greatly benefited by this program. Thank you very much.
Thank you very much, sir, for your kind and motivating words. Thank you for your blessings too. Gratitude is the fairest blossom which springs from the soul. I call upon Dr. M. Manivannan, Associate Professor, Department of Electronics and Instrumentation Engineering, to acknowledge everyone who has contributed for this function.
Very good morning to all. So it gives me an immense pleasure to propose vote of thanks for this event amid of the dignitaries. First of all, I would like to thank our head of the department and my beloved teacher, Professor Dr. R. Kailviri, for all her support and guidance in organizing this event. I would like to thank our senior professor and our academic grandfather, Professor Dr. K.N. Bhatt, and my beloved teacher and my research supervisor, and Dr. Joseph Daniel, for sharing their inspirational thoughts with us and among the participants. So I'd like to thank Professor Dr. V. Balasubramaniam, Head of the Department of Manufacturing Engineering, for permitting us to use this video conferencing facility. And I would like to thank Dr. Rajakumar, Professor Manufacturing Engineering, for his splendid support in organizing this event. So I would like to thank the faculty members, staff members who are behind the screen for their support and guidance in making this event a grand success. So I would like to thank the participants and the experts in the field of NIMS who are going to share their expertise with the participants throughout this program in advance. And I thank everyone again for making this event a very successful one. Thank you, sir.
Thank you so much, sir. And thank you all for joining in the inaugural meet. Now we are moving into the first session.
Hello, sir. Thank you, sir. I thank Professor K.N. Bhatt, sir, for spending your valuable time for us. I thank you once again, and I thank our beloved respected Professor Dr. R. Joseph Daniel, sir, for accepted my invitation. So thank you, one and all. So. Okay, sir. Thank you, sir. Thank you so much. So shall we move to the session, sir? Thank you.
It's my pleasure to introduce the resource person of the first session. The resource person's name is Dr. T. Ramesh. He's an associate professor in the Department of Mechanical Engineering in National Institute of Technology, Tiruchirappalli. Dr. Ramesh has completed his UG BE Mechanical Engineering in Madras University in the year 1995. Then he did his master's in the Bardea University in 1997 and has completed his PhD in 2006 from Bhardhidasan University. He has a good work experience. He has been assistant professor in Jairam College of Engineering and Technology, Thurayur, and in JJ College of Engineering and Technology, Tiruchirappalli. He's an assistant professor in National Institute of Technology, Tiruchirappalli, and now an associate professor in National Institute of Technology, Tiruchirappalli. He has published more than 45 papers in international journals and 4 papers in national journals. He has produced 7 PhDs and 7 PhDs are ongoing under his guidance. He has handled many projects successfully. Some of his projects are experimental investigation and finite element simulation of workability of TIC metal matrix composite during cold upsetting. And it's a It's a project completed with a fund from DST, and he has also completed some projects from Blast, DRDO and from NLC Neyveli. Adding to these, he has published 2 books. Now, Dr. T. Ramesh will deliver his lecture on research scopes and MEMS. I hand over the session to him, please, sir.
Hello?
Hello.
Is it audible, sir? Can you hear me?
Yes, ma'am. Yes, ma'am.
Okay.
So already.
Are you able to see my screen, ma'am?
Share your screen, sir. PT.
So it was shared.
Sir.
Hello.
Full screen. Yeah. Now it is okay, sir.
Share, sir.
Am I audible, ma'am?
Yes, sir.
Okay.
But,
Just a moment, ma'am. I'll check this.
sir, please start your session, sir. No problem. Already we are introduced.
Okay. My camera is visible. Is it on? I don't get this detail.
Hello.
Yes, sir. Visible.
But your voice is not that much audible, sir.
Hello.
Yeah, now it's okay.
Okay. So, very good morning to Varna. It is a pleasure to associate with. I hope first time. The ELA department of Anomaly. I had many opportunity, or I had given many opportunity to the mechanical and manufacturing departments. I think this is the first time I am associating with the ELA department of Anomaly University. Thank you, Daniel sir. I think thanks for remembering me. We attended one program at Pondicherry Engineering College during 1998. I hope if my memory is correct. I thank the organizer Dr. Ma'am for fighting me as a resource person in this particular field because I have started working in this particular field a few years back. Anyway, we have done quite a bit of work in this particular field, not in the electronic side, but in the mechanical field. See, today's topic is a kick-off lecture of this particular faculty development program, research scopes in micro electromechanical system. So this particular presentation is prepared in such a way that the people who have started to think on doing some research in the particular direction, like MEMS devices. So I have collected the basic information about the micro electromechanical system in this particular lecture. End up with some case studies which we have conducted in our laboratory. What are the outcomes of those case studies that we'll discuss a bit later. So today's lecture is organized in this sequence like introduction to MEMS. I think I will spend more time on this particular topic. And then applications of MEMS, especially in automotive sectors, biomedical engineering, and critical sensors. And there are a few case studies what we have carried out in our laboratory, like developing a micro gripper, adopting component mechanism technology. Once again, it is developed by toeq optimization technique. So this micro gripper is identified as one of the best mechanical advantage so for taking minimum input, it will behave in a very drastic way. So the mechanical advantage is higher. I think we will see the design aspects and the way how we fabricated and tested in our laboratory that we will discuss. And then micro cantilevers, an unavoidable device, mechanical device found in MEMS application in many situations. This particular micro cantilever is developed for understanding the ripening rate of fruits that was developed in our laboratory. And then micro joining of plastics. We know that the plastics are highly involved in packaging of MEMS devices. The available facility like micro laser cutting machine, we used that particular machine for performing the joining of plastics. An interesting work done by BTech students along with PhD staff. What has not been completely done, but a part of work I will show you. And then another important device we procured from our own alumni, my own student, who is a chairman of an industry or design center called Micron. Bedplex is a company name. He developed, this is a PhD work of Dr. Ramnath Babu. He's my student at NIT Trichy. And he parallelly worked with Dr. Andhra of IIS Bangalore, who is the inception of this particular area. He is always a good for me. He completed his PhD under his guidance, and his PhD is converted as a patent. Am I audible? Hello?
Sorry,
Okay, perfect. So micron tester, I think some echo is coming. I don't know. Hello. Okay. So these are the research facilities we procured recently for developing student innovation center at the time of Trichy at a cost of 1.151 crore. Somewhere system, now it is okay. So we procured recently the following equipments for our student innovation center, the cost of 1.1 crore. PCB routing machine with microelectronic assembly.
Sir, kindly unmute yourself, sir.
Ramesh sir.
Hello.
Now it's okay, sir.
Okay.
Now you can continue.
Yes. It is capable of printing 0.1 because 100 micron thickness, thick layer of a material. It is possible to reinforce with many materials like carbon fiber or the glass fiber or Kevlar, whatever it is. And then another equipment we procured recently is a shining 3D scanner, which is used for as reverse engineering of any mechanical components. So it has a resolution of 40 micron. Also, it is integrated with the Mimix biomedical imaging software. Whatever the image we scan with the 3D scanner, that could be converted in the form of 3D models for further final element analysis. So Mimix is a biomedical imaging software which is capable of converting any 3D scanned images. It may be a 3D scanned image or it's an MRI scanned image or CT scanned image, whatever the image format can be converted into a 3D form. Also, we have extended our research facility in IntelliStudent for the Student Innovation Center with additional licenses. Apart from this, we have many equipments. To start with, micro-electromechanical systems represent a very important class of systems having applications ranging from small embedded sensors and actuators, passive components in RF, and microwave fields, and micrometers in the optical fields. So the importance of MEMS stems from their many advantages. There are many advantages I think I will list later. But among which, so these are the predominantly considering as important that of many other advantages, like a small compact size amenable to integrate with other components. That's a very important advantage found in MEMS design. Low loss as well as parameter variability. So with these advantages, the MEMS keep on enhancing its applications, spreading its application into multiple domains, starting from mechanical to biomedical engineering nowadays. So in order to understand the size of the device, I think this is a quite common pictorial representation used by many researchers to illustrate that how the MEMS technology is falling between a nanoscale to macro scale, mesoscale. So it is well understood that the technology has been divided into a number of categories, starting from nanotechnology, we have microtechnology, and then we have mesoscale technology, and then macroscale technology. So when nanotechnology, we know that it starts from a few Armstrong to and ends with a few nanometers, nanometers. The viruses are falling in the category of nano size component. And then the micro-electromechanical systems are microtechnology following the range, the dimensional spectrum range of a few nanometers to a few millimeters. Quite a good example is human hair, which is around, whose diameter is around 40 to 60 micrometer. So now the challenge for the designer is to develop such a small device in this dimensional spectrum. So starting from few nanometers to and ends with few millimeter. In the mesoscale, it starts from few millimeter and then ends with few centimeters. And then the macro-sized technology is varying from few centimeter to few meters. So human is an example. Which is a collection of many technologies, starting from nano to MEMS, micro to meso, and then macro technology. So any engineering system that performs electrical and mechanical functions with the components in micrometers is the MEMS. I think it's a precise definition of MEMS. It should have the functionality of both electrical and mechanical. That is very important. Otherwise, we simply call it an electrical device or mechanical device. So it should have electrical function as well as mechanical functions. Then only it is called MEMS. So the available MEMS products include micro sensors, especially used in biomedical, chemical, pressure, and then radiation, thermal, etc. Micro actuators. So starting from valves, pumps, grippers, tweezers, and tongs are the great examples of micro actuators. Real-time heads in computer storage system is another important product where you can find a collection of MEMS products. Inkjet printer heads, where microheaters are used to heat or to create a vacuum in the ink carriage zone, so that the nozzle will be supplied a subsequent amount of fluid to flow through it. It is all because of MEMS devices like MEMS heater. It will create a bubble. So that bubble will produce a necessary vacuum for oozing out the ink through the printer plates. And then micro device components. So starting from mini robots and toys, microsurgical. So the picture I have shown over here are the examples of various micro devices developed by many researchers around the world. So the first one is a micro B developed by MIT, whose responsibility is to fly in the sky and surveillance the activity of unwanted persons. Right? So it has attached with the feathers. Right? There are white colors feathers attached with it. The size is compared with the aircraft. Now, so this device will have integrated devices like energy storage system, actuators, micro camera, and then micro sensor, micro transmitter. So all these devices are integrated in this particular domain, so that this will be controlled from ground, and it will fly, or it will be permitted to fly near the borders of the countries. So the next one is a coupling mechanism based micro gripper developed by Once again, it is a US University, Pennsylvania State University. And the size is measured over here. So this lake is equal to 1 millimeter. So you just understand how many systems are involved over here in order to make these two jaws move together or away from each other. So its responsibility is to hold tiny objects, micro objects or nano objects, or any fragile substances or blood cells for manipulation. So all these functionalities, this particular microcontroller is used. Now it is well understood that there are no joints. It's completely working based on component mechanism concepts. That is a different concept. If you are interested in just search through media. So this client has a small footprint, microflow air pressure sensor in the world. So the size is compared with the pencil tip. It is capable of sensing the pressure variation of the air within the environment. So it is very important device. And this is another important device found in the airport to sense the unwanted movement of any chemicals carried by the passenger. Dr. Ramgopal Rao from IT Bombay is involved in this particular development of this particular device. Once again, they have used mechanical, what do you call this, micro cantilever as a catalyst for sensing the variation of any environmental changes in the system. So I attended a program at IT Bombay conducted by Ramkumar Rao on explosive detecting devices based on EMOS technology. I think I'll tell you the concept behind this particular device. And it is a single lab on chip where you can find many applications of micro activities like micro sensing of pressures, flow, temperature, humidity, etc. So normally we call it as a lab on chip. A small, very small device. I think I switch my camera on. I mean, you see a device of hello. Hello.
Sir?
So camera is visible now?
Yes, sir. It is visible.
The new device.
It is visible, sir.
Your hard disk is available?
Yes, sir.
Okay. So it's a internal details of hard disk, and this is a surface where the data are stored, and it is a cantilever kind of arm which hold a small, tiny particle-like substance called stylus by means of the micro dipper. So the tip is a micro dipper. And what normally it will do is very similar to a record player in our old system. It will scan the location where the data is available, right? So this point or this tip is called the stylus. The distance between this surface and the stylus is maintained as few nanometers. Now it is completely controlled by means of this electrostatic motor. You just think about how it is maintaining the what do you call this, the gap, not the air gap. We call it as nanometer size of gap. right? I think when it is focused, we'll see details of micro. Yeah. So this is the one. Now the micro grippers are attached. And it is the actuation is given by means of this particular nanowires, right? Okay. So when you see on the back side, it is a collection of microelectronics. You just think about how this is being connected. A small strip-like section is used to connect this. Right? So it is a collection of many electronic parts. A transistor or what the capacitor or whatever the electronics is. So then that's a question like, what is a MEMS technology? So it's a technology that in its most general form can be defined as miniaturized mechanical and electromechanical units. So the word called miniaturization is very important in the case of micro-electromechanical system. Miniaturization in the sense, it is a miniaturization of devices as well as structures. So there are made using the techniques called microfabrication. So the conventional fabrication techniques in the macro domain will not help us scale down to some particular dimensional spectrum. So the critical physical dimensions of MEMS device can vary from well below 1 micron on the lower end of the dimensional spectrum all the way to several millimeters. So the types of MEMS devices can vary from relatively simple structures having no moving elements to extremely complex electromechanical system with the multiple moving elements under the control of integrated microelectronics. The one main credit of MEMS is that there are at least some elements having some sort of mechanical functionality. Whether or not these elements can move. The term used to define MEMS varies in different parts of the world. In the US, they are predominantly called MEMS, while in some other parts of the world, they call the microsystem technology or micro machinery devices. So these MEMS devices are fabricated using integrated circuit batch processing techniques, and these devices have the ability to sense, control, and actuate on micro scale and generate effects on the macro scale. That is very important. The sensitivity is measured in terms of micrometer, but we need the output in the form of macro scale. So MEMS consists of mechanical microstructures, microsensors, microactuators, and microelectronics, all integrated onto the same silicon chip. So the MEMS is a combination of all these, like starting from microstructures, microactuators, microsensors, microelectronics. So what is the responsibility of every system available over here is the microsensors direct changes in the system environment by measuring mechanical, thermal, magnetic, chemical, or electromagnetic information. Now, the sensor will respond to the environmental change. That response will be sent to the microelectronics for processing. The microelectronics process the information received from the microsensors. It will process it based on the output. It will be it will send a signal to microactuators to actuate some element in order to nullify the effect of that particular environmental change. Say for example, assume that you are sitting inside a cabin of a car, And that particular car is integrated with MEMS functionality. See, you feel that the temperature inside the cave is not sufficient for your comfortness. Then automatically what you will be doing is you will reduce the, or you will increase the reduce the temperature or increase the airflow, right? Now, the automatic air conditioning system does the same process, like it will change the environmental conditions. It will sense that the temperature is comfort to the passenger or not. Then you will develop some mechanical functionality. Either a rotation or a movement, there is a displacement, vibration, whatever it was. So that signal will be sensed by microelectronics, and then it will send a signal to microactuators. Here, the microactuator in the form of, say, electronic media or mechanical device, whatever it is. So it will reduce the temperature, increase the air pressure flow. So all these systems are sit on a structure called microstructure, and this is a combination of or a collection of components. It's a assembly of all these systems are called MEMS. It's integration of all sensors, actuators, electronics, and microstructures. We call it simply as MEMS. So MEMS devices are very small. Their components are usually in microscopic scale. For example, levers, gears, pistons, as well as motors, and even steam engines have all been fabricated by MEMS nowadays. So however, MEMS is not just about the manufacturing of mechanical components or making things out of silicon. It's a manufacturing technology, a paradigm for designing and creating complex mechanical devices and systems, as well as their integrated electronics using batch fabrication techniques. So these are the examples of MEMS devices. I captured from Google image, like it's a gear train, and this is a turbine. This came out of running at a velocity of 30,000 RPM, 30,000 RPM. You just compare the size. So this length is equal to 50 micrometer. This length is equal to 50, approximately this is equal to 40 microns, right? So when I see the components of MEMS, as I was mentioned, it's a microsensors, microactuators, microstructures, and microelectronics. And this is the way how the microsensors is working, like a pressure sensor. I think we'll rush through this because I have a limited time. And this is a microactuator. Mimics the heartbeat of a human, and this is a microstructure, and here we have a assembly of microelectronics. There are three important words normally used in mechanical system: a transducer, a sensor, and actuator. Let us have some idea about what is this for the people who is new to this field. A transducer is a device that transforms one form of signal or energy into another form. The term transducer can therefore be used to include both sensors and actuators, and is the most generic and widely used term in use. A sensor is a device that measures information from the surrounding environment and provides an electrical output signal that is the part, which should produce electrical output, otherwise it is meaningless. See, over the year, this information or phenomena has been categorized in terms of the type of energy domains. That MEMS devices generally overlap several domains or do not even belong to any one category. So when I see the energy domains, we have a mechanical domain, thermal domain, chemical domain, radiation domain, magnetic domain, electrical domain. Now sensors used for sensing the force, pressure, velocity, acceleration, position. Our sensor will be used for applied in the thermal domain, not to sense the temperature variation, entropy changes, heat losses or heat gain, heat flow, etc. Concentration of chemicals, combustion of chemicals, reaction rate can be sensed by means of a sensor categorized in chemical domain. Radiant, electromagnetic wave intensity, measuring phase, wave change, wavelength, polarization of reflectance, refractive index, transmittance, etc. Or it may measure the magnetic field intensity, flux density, magnetic moment, permeability. Or it can measure, it can sense the change in the voltage, the current, charge, the resistance, capacitance, polarization, etc. An actuator is a device that converts an electrical signal into an action. So it can create a force to manipulate itself, other mechanical devices, or the surrounding environment to perform some useful function. So the sensor is supposed to have two major properties. It should have maximum response to whatever it is to be directed. In other words, large sensitivity. It should have a large sensitivity. And the second important property is no or very small response to all other inputs. In other words, very small cross sensitivity or high sensitivity. Suppose a sensor is designed for sensing the changes in the environmental pollution. It should have large sensitivity against the environmental changes with a small cross sensitivity like pressure or rainwater response. It should not give response to those cross sensitivity. Or it should have a high selectivity. Selectivity in the sense it should respond to the particular environmental changes. Environmental changes in the sense changes in the chemical composition of the air. Any additives are added in the air domain should have a responsibility. So how it is possible to design such a high selectivity or large sensitivity devices? That is an interesting information we have in the design of mainstream devices. Now this is a simple idea about a sensor. So whatever the input it should have, it should produce or it is capable of producing electrical output, either in the form of voltage or current. Input may be of mechanical, optical, magnetic, or thermal. A sensor is responsible to convert the signal received from the input and capable of producing electrical output. So what we need to have inside the sensor is some kind of director coupled to something that produces the electrical signal. So how it is being done? So assume there is a resistor which is kept on a microcantilever. Now the cantilever is capable of producing mechanical output like bending or in the form of displacement. Displace the form of bending. Now the resistor will loosen its resistivity or gain its resistivity, by which it produces electrical output. Say for example, if I apply a load here, this cantilever will try to bend, right? Which will increase the resisting area of this particular device. So what will happen is the changes in the displacement is converted in the form of electrical resistance. So here the red material converts the deflection of electrical output. This resistor may be in the form of piezoresistive material or piezoelectric material, like a quartz or PZT. So the piezoelectric material has a very good property of producing electricity when it is strained, right? When it is subjected to mechanical strain. So once the cantilever bends, what happens is the top layer will get stretched. Means that the material laying over that particular surface also will get stressed or strained, right? So because of this strain, electrical signal will be produced. So this is the one such kind of sensor normally be used in MEMS applications. Or it may be of changes in the measure the change in the capacitance. It says sense electrodes are integrated with the cantilever beam. When it starts vibrating or moving, the gap between the microcantilever and the sense electrodes are changing because there are no fluid is filled within inside. It is in the form of air or any other medium. Fluid medium is introduced. So now the change in the capacitance is happening. So that capacitance will be measured and taken as an output for sensor. Similarly, we have magnetic and inductive sensing, which is possible if one uses a ferromagnetic material like nickel on the cantilever. Or optical methods, this might be used, but once more not easily in silicon MEMS technology, or it is of a thermal transfer. In contrast, might be used with silicon MEMS, but not so much for detecting reflections of beams and membranes. So MEMS sensors are already developed in many forms and available in the market in the form of accelerometers, inertial measurement units, magnetometer, pressure and inertial sensor, pressure sensor, airflow sensor, fuel sensor, impact and crash sensor, MEMS microphone, temperature sensor, etc. So flow sensors are required to measure the rate and direction of liquid and gas flows in various applications, including determination of flow patterns, measurement of wall shear stress, viscosity and density measurements. So these are the areas where you develop devices, MEMS devices for measuring a flow direction of a liquid or gas flows. I think one such developed device helped a lot during this particular kind of situation, the human breath analyzer, right? So it immediately detects what kind of or what is the level of oxygen you have in your breath. Whatever the information available that could be sensed by means of this particular device. Then MEMS actuators are in the form of electrostatic, thermal, piezoelectric, and magnetic. So some electrical input produces an action. So of course, the action might be the production of magnetic field, light, or some heat, but usually it is a mechanical movement. So this can be induced by producing a force that pulls or pushes at something directly, or by just producing some pressure that acts on all surfaces. So MEMS actuators are the type of electromechanical systems that convert energy into motion. Let us see some examples of various MEMS actuators developed around us. So we have a top drive, which is working based on electrostatic actuation system. A scratch drive, parallel plate uniform, distributed electrostatic devices, repulsive force, electrostatic relay, etc. Or piezoelectric, maybe in the form of BIMOP expansion. A thermal, we have a BIMOP, solid expansion, topology optimized, shape memory alloy, fluid expansion, and then state change, thermal relay, etc. And we have a magnetic in the form of electromagnetic, magnetostrip, external field, magnetic relay. And this is one such example of BIMOP cantilevers used as micromechanical linear actuators. You can see that there are two different materials are combined over here in order to understand that for a particular temperature it will expand differently, right? Because of the linear expansion coefficient, thermal material property of this material, this will expand differently. So such kind of combined materials are, different materials are combined in order to produce such a particular boom, right? So this is a deformable mirror developed by Boston. And when you see the advantages of MEMS, as I was pointed out, apart from those two important advantages, we have many advantages also. See, the cost, low cost mass invention. The size of sensors or components will be 1 to 100 micrometers. So the device size will determine 20 micrometer to a millimeter range. So power consumption is very low. Simple and incorporated into systems or changed. Thermal constant is very small. So this can be highly opposed to shock, radiation, vibration, because those effects are severe in the case of a macro dimensional spectrum. Better thermal development tolerance, and also a parallelism is maintained. So when you see the applications of MEMS, it starts from automotive, electronics, medical, communications, defense. There are large amount of area where I have left out over here. You can find MEMS devices in many applications. So for example, in automotive sector, say for example, air conditioning compressor sensor, fuel level air temperature sensors, airbag sensors, intelligent tires are the recent developments in the area of automotive. So we know that how comfort our cars are nowadays, and there are many MEMS devices found inside. So electronics, the case of disk drive heads, inkjet printer heads, projection screen, television, backpack sensors, avionics, etc. Then in the biomedical area, we have blood pressure sensor, muscle stimulators, and blood delivery system, plant pressure sensors, etc. etc. There are so many applications we have in different domains. But MEMS takes greatest advantage in the area of electronics. We know the clarity of sound we hear with our earphone used in Nokia and Apple iPhone 12 Pro, right? Now earbuds are available. Earbuds are available, so you just know the clarity of the sound. So especially in this particular electronic field, it has extended its application in a many drastic way. So starting from cell phones, earphone headsets, medical applications, automotive, IoT, consumer electronics, laptop notebook, etc. Especially in the case of smartphones, it is a very new MEMS development. So starting from, we never thought about a thermal imager will be integrated with mobile phones, right? We never thought that video chattings are possible with the help of micro cameras, and MEMS cameras inside the smartphones. So because of the MEMS devices introduced in the smartphones, we are capable of hearing enhanced sound, navigation and environment sensing is possible, and then tactile interfaces are nowadays available, infrared sensing, improved visual experience, and then increased battery lifetime, better communication performance. Everything was happened because of the enhancement in the MEMS devices. So one such example I want to show here is a LED backlit LCD display of a smartphone. So it's a combination of, I'll show you the screen, LED screen of a smartphone with a different layer. So this is a one, we call it as a LED display. But it is not only taking responsibility of showing the pictures or the videos, but once I touch here, it is capable of working as a pressure sensor, am I right? A pressure sensor or a touch screen. So the thickness is the thickness of this particular assembly is this much, but it is made of different layers, right? So this is the pressure sensor. So all these are assembled as a single unit and will act like a single unit. And this is one such example. It's once again a touch sensor used for bringing your home screen in the iPhone, am I right? And we have a micro camera. You just see here. So this is the one. A micro camera. And see how it is being connected. There are microphones here, am I right? So all are assembled in a single wafer-like structure. Now, one thing is, say how it does its autofocus. That is very important. Another MEMS technology found inside, which is capable of adjusting the clarity of your picture. Am I right? So this is an LCD panel behind which we have a brightened enhancement films. Below which there's a diffuser and that's a light guide, LED housing, back reflector, backlight unit. So it's a combination of all these things. So it is act as a single unit when you see in the smartphone. So MEMS application is extended its use in a biological and medical applications where you can find lab-on-chip, cell sorter, cell gripper, etc. In the case of energy domains, now people are working in the area of fuel cell harvester, radio frequency, oscillator resonator, pressure sensing like the tire pressure, microphone, filter head, etc. Accelerometer gyroscope compass, inertial sensing is used. And then the projector, micro display mirrors are developed, adapting optical transmitting technology. So all these things are because of the MEMS technology. So MEMS technology contains a broad variety of MEMS sensors that is widely used in automotive industries. So MEMS market is the second largest market in the world. As compared to the conventional sensors, MEMS sensors have advantages like fuel utilization reduction, safety advancement, and is economical to vehicles. Now, to show the importance of the MEMS devices in the automotive sectors, I have taken this picture from printers. You just see how many sensors are integrated in your racing cars. So starting from airflow sensors we have here to check the quality of the air which is taken inside the engine manifold. Air pressure sensors to monitor the pressure level of the air. Air conditioning compressor sensor in order to find out the quality of the air which is getting inside the pressure. Inside the compressor. A transmission fluid pressure sensor, navigation sensor normally used to find the navigation of your navigation application for your car. Inertial navigation sensors, we have temperature sensor so that it will predict what is the temperature inside your cabin and outside surrounding. So both will be displayed in the control panel, am I right? Airbag side impact sensor. Once it finds unwanted or a sudden impact, this will release the airbag. in order to safeguard the passengers as well as the pilot. Mobility sensor, we have exhaust gas sensor, pollution detection sensors, NOx sensor, fuel level sensors, vapor pressure sensor, etc. Then crash sensor, door side impact sensors, seat belt sensor, brake sensor, airbag sensors, tire pressure sensor, monitoring, force sensor, brake sensor, etc. etc. There are number of medical devices found inside your class. Because of those sensors and actuators, we are traveling in the car nowadays very comfortably. So one such example I want to put here is a pressure sensor available inside the tire. So which is embedded inner surface of the tires. Once any changes in the air inside the tire is happening, that will be sensed by means of this pressure sensor, and that will send a signal to the control panel, say that the left front tire has this pressure, air pressure is this pressure, right? TPMS is a new technology introduced in the recent cars, tire pressure monitoring sensors. I think so. This is another picture illustrates the importance of many MEMS devices. Some will be left out. You just think on your own, you design the requirement of the passenger, and then develop a new device. Yeah. I will let you. Yeah. So there are two important facilities available in recent cars. One is ESP and the other one is HVAC. One is ESP in the sense electronic stability program, which provides you with two other active safety systems. One is anti-lock braking system, and the other one is traction control system, ABS and DCS. Another important area is HVAC. HVAC is heating, ventilating, and air conditioning. It's a technology of indoor and regular environmental comfort. So its goal is to provide thermal comfort and acceptable indoor air quality to the passenger. And the tire pressure monitoring system is an electronic system designed to monitor the air pressure inside the pneumatic tires on various types of vehicles. Nowadays, we have in the area of automotive sector, we have compliant tires, compliant mechanism tires, where we never require any air inside. That is another recent advantage, the development in the area of automotive sector. We don't want any tubes or air inside. Instead, we have a compliant mechanism, which takes the responsibility of the material alone. The material alone will take responsibility of the functions of air. It both the load as well as when it rides on a bump, it will take the vibration. Okay. So, MEMS in, yeah. The other area where the MEMS is recently tapped into is the MEMS in biomedical engineering. So, biology and physiology research and clinical medical care often require small, lightweight, fast response, and easy to operate equipment and process that can also be mass manufactured at low cost. So, this is a requirement of any biological and physiological research. We know that the MEMS products, when it is incorporated with microelectronics, integrated circuits, and computing blocks, can become a small volume, low power consumption, online analysis, and a quick response equipment to safety the needs of biological research and clinical care. So these are all three classes of biological applications of MEMS, like research in biology, medicine, and pharmacology, individualized medicine, or improved medical care to patients. So in all these three classes, MEMS are required. Research in biology, medicine, and pharmacology. So individualized medicine, it is available in the form of tablets. Normally we call it as drug delivery system. individualized medicine. They include medical characterizations. So when you see the MEMS in biomedical area, there are many researches going on nowadays in order to study the human behavior or the parts of the human. With the help of a pressure sensor installed near the brain, it is possible to measure the magnetic, the wave pressure. I think the studies are going on. Cardiac sensors are already established. GPS sensors are already established. Muscle activity sensors are already established in the biomedical realm. And also it is possible to measure the capacity of your lung with the help of a sensor. So this is one such example where you can find the applications of MEMS in a biomedical realm. So Boston University has conducted research in the area of retinal implant, which is an array of subretinal area of a pig that affects most of the processes, the titanium and the other electronic assembly. Now it has been implanted on the outer surface of the human, the pig eyeball, and study the changes, whatever the measurements it is, thermal changes. There are many studies going on in this particular domain. So the recent development is a soft flexible cardiac sensor. It's a thin elastic enclosure and data transfer to a smartphone app, which can be bent. So it will be weird as a very similar to a bangle. So this is a new development in the area of biomedical engineering. And then in the case of drug delivery system or surgical applications, the MEMS used in the form of micro robots. So here is an example. So there is a small micro robot, which contains information about all these parts like a camera, LED, lights are there, exhaust ports, etc. So the drug will be filled and sent inside your body just by asking the human to swallow it. And then the movement of this particular micro robots are controlled from outside through magnetic waves or electromagnetic waves. So once it reaches a desired location where the drugs are to be delivered, there we will send a signal to the micro robot to explode. Right? It will be exploded and effectively transfer or deliver the drugs. Right? And this is one such micro robots used for surgery operation, surgery purposes. So the rotation linear movement of this particular micro robots is controlled from outside. So when it reaches a particular location, it will be triggered and appropriate rotation will be given to remove the amount of the tissues from the tissue. And MEMS is also used as a biopatch for measuring and collecting vital information through the skin. It is inexpensive, versatile, and comfortable to wear for the user. And data being gathered depends on whether it is placed on the different parts of the body, like the chest, skull, forearm, etc. When this particular biopatch is stick near the chest, it will act like electrocardiography. And when it is a stick near the skull, it acts like a EEC, that is, it measures the brain waves. Apart from the human, the MEMS is extended its application to find the wildlife tracking. There are beautiful videos available in YouTube. You can find how the locomotion of this particular cheetah is studied by means of a MEMS device, micro camera, which is installed over there. And then there are devices attached to it. So besides common diagnostics and treatment, the MEMS system can have important applications in orthotics and prosthesis. So besides artificial limbs, by implementing functional electrical simulation and the neural control techniques, MEMS may be used in visual prosthesis, hearing aids, cochlear implant, electrical stimulation for pain suppression, diaphragm pacing, heart pacing, and deep fibrillation, bladder control, etc. etc. There are so many locations where we find the application of MEMS. So similarly, in the future, artificial organ or organ repair will benefit from implantable MEMS system for monitoring actuation and control. Say for example, suppose I have a surgery and I have been replaced with a new implant in my leg, right? So now I want to study the information about how the degradation of that material is happening. So what is the amount of force which is being transmitted from my body to the implant and then implant to the bone. So such kind of information can be captured by implanting another MEMS device inside our body. So it is used for monitoring, or suppose I have a system inside, like blood delivery system. I will be clearing the blood delivery system and then it will transfer to the delivery to the body. So it is possible to integrate in the future, and we have a certain living example nowadays that they live with artificial informations. So MEMS in chemical sensor, which is capable of converting the non-electrical parameters into electronic compatible signals. Chemical sensors are image-based devices which convert a chemical state into electrical signal. So this is a quite example that explosive vapors are detected by means of a microcantilever. So this is how a MEMS device is used. Say for example, this particular microcantilever, when it is in equilibrium conditions, it will be straight and now it has been coated with many materials. One is especially for converting the displacement into electrical signal, and the other one is a material which is attracting a specific chemical. Now, so this is the technology used in explosive reactors, chemical reactors. When the vapors are coming and mixed with the air and flowing around this cantilever, the material which is coated over there is very attracted to the vapors, explosive vapors. So those vapors will be attracted. So what happens? The vapors will come and rest on the top surface of this particular layer. Obviously, this will enhance the weight of this, or it will act like a forcing medium to make this cantilever to deflect. Right? So once this is deflected, so because of the material coated on the top surface, also will be stretched. Now, as this is a strain or a stretch, it will produce a voltage. So this is how the microcantilever is especially used in chemical sensors. You can find such kind of sensors in many applications, starting from blood discovery and life sciences research, food analysis and storage, fragments and flavor analysis, the chemical industry, medical diagnostics, agriculture, environmental monitoring, security devices, detection of hazardous and explosive substances, study of chemical reactions, etc. So this is one such kind of cantilever being developed by researchers. I think I'll put this reference in the next slide. So microcantilever belongs to a class of mechanical system device that encompass all those devices produced by micro application. It responds to the integration event by mechanical information. So this is a way how it is being manufactured, and then what are the materials available on the top surface of the microcantilever. So it is high sensitivity, the possibility of integration of transducer, actuator, and readability of the same. So this is a piezo-resistive microcantilever over which piezo-resistive silicon is operated. Alright. So the cantilever bends due to surface stress, changes in the resonance frequency due to additional mass load. So microcantilever arrays for improvement of circuit. And we have developed the microcantilever. So this is the one. As I was mentioned, like explosive vectors are working based on a technology called EOS. Ramkumar worked in this area. So electronic dose is a device which is capable of sensing the odor. Sensing the odor is possible. So how the human knows differentiate odors. Such kind of analysis is possible. Such kind of making a device is possible. So what we require in a human system, we require a odor, which is the form of a smell, and we need a record of information in the drive, and we need neurons for comparison. Right? Suppose you are sitting in front of a coffee, right? The smell is coming and it's in the air, and this is the nose system. So now the nose acts like a sensor. It will send a signal to the drive. I have received a new odor. You just tell me what kind of food it is, right? Now the data are saved in the form of patterns in the drive. So neurons will do comparison of the recorded data in the drive, processing, and immediately send a signal to once again that it is a odor of a coffee. Now very similarly, there are raw signals available in the environment, and it is to be processed, and there are neural networks used for comparing the information. Now, let us take an example, like there is an explosive material available in the air. So now, what happens is, the cantilever attracts those vapor so that it will come and rest on the top surface of the cantilever, which will produce a surface stress. Alright, so this will bend. Now, for every vapor, we have a mass, and for every mass, it has a defined deformation. Alright, so those deformations will be recorded in the process data, right, in the form of data. So for this particular chemical, so this is the mass and this is the deformation. So those will be recorded in the system. So once a new material is coming and mixed in the air and is detected by means of microcantilever, it will produce the information. So that information will be taken as the input for processing. So it will compare the amount of information happened with the help of neural networks and say that this is a recognized pattern. So this is how the EOS technology is used. And I think for the case studies, I just quickly run through because I have only 5 more minutes to complete this presentation. If time permits, I'll extend my talk. So I have shown a micro gripper which was attached to the cantilever arm of the participant. Right? Similarly, so we have developed a micro gripper used for biomedical applications. Like this micro gripper is developed for actuating the blood cells, right? You can find that. So this is the final topology of our micro gripper, and it was fabricated in steel, biocompatible with the. So we have a drilled hole here, or the input force will be given over here. And this location is pulled in this particular direction. What will happen is the jaw will move closer to each other. Right? At the same time, if I give a negative force like opposite directional force, the jaw will move away. Now it is quite interestingly, there is no joint. The material flexibility is used as a joint for this particular mechanism. So this is the experimental setup we have developed in our laboratory. So this is a micro gripper attached with the shape memory wire. This is the wire, and it will be triggered by means of vertical circuit. Now the SMA wire is act like a actuator, so it will produce the force for opening and closing the jaws. Right? The movement of the jaws will be captured by through microscope, and we have a experimental setup in our laboratory. Now this is the experimental setup. This is a driving circuit. When I trigger, electrical potential will be supplied to the SMA wire. SMA wire is manufactured in the sense in the way that when it is heated up, it will get contracted, right? The length will be shorter. So once the length is shorter, what will happen is it will move in this particular direction. It will produce the necessary force on the particular location, by which we achieve the necessary movement in the jaws. So this is the manufactured micro gripper from stainless steel G16. This is a biocompatible material, 1 mm thickness. It is measured through bioacademia for the design sheet. So apart from this, so this is the micro gripper, which was developed by us for a PhD work. And these are all the other type of grippers. Can you see it? I think I will hold it. Right? It is completely operated by means of thermal expansion coefficient. It was developed by a student team that came for internship from IIIT Andhra Pradesh. So this is another micro gripper. So this is a cantilever produced for that are understanding the ripening of a fruit. The thickness is 300 microns, and the length is nearly 12 mm, 12 to 14 mm. You see the aspect ratio. The thickness is very small. It's 300 microns. Okay. So for medical purpose, we developed this gripper. We have conducted a severe experiment on this device, and also it was simulated through 5mm analysis package. And this is another type of gripper we developed in our laboratory. So from initial design, rectangular block, this micro grippers have been formulated. Now it has a three arms like it holds so it is developed for folding the circular object. Right? So this is another micro device we developed. And this is another type of grippers designed and manufactured for particular applications. So here, a biome of a differential, electrical potential is given to the material so that it will expand differentially, based on which the upper and lower jaw will move. Right? It is used as a tweezer for many applications. So this is the total displacement and the surface temperature distribution, one-way stress distribution of this particular gripper jaw. So this is the micro cantilever. What I have shown was connected with the vibrational testing facility. So interestingly, the facility is created by spending very a small amount of money. It's a vibration speaker. We bought from Mezan, and that is act like a vibration generator. We downloaded necessary signals from the YouTube, sound waves from the YouTube, and we have given as an audio file here to make this vibration, to make this speaker to vibrate. So this is the cantilever. It was installed in the actuator. Our vibration generator, whatever we call, and this is the actual setup. The movement is completely captured through the microscope. The values are compared with the micro profiling element analysis. We understood the various mode shapes of a micro cantilever, and we exactly mapped with this particular cantilever. So this is the way how we capture of the vibratory waves. Now you can see the motion. It's exactly mapped with the final solutions. And this is another interesting work we have conducted in our laboratory. Joining of plastics, especially using MEMS packaging devices. So this is the CO2 laser cutting machine facility available in our laboratory. It is designed for cutting the polymers, but we are using it for joining the plastics, joining the plastics. It's a reverse of the purpose what the machine is made for. Yeah, I think this is the modeling simulation of microjoining process. So from which we understood what is the power we require to melt the material. And this is the way how it was fabricated. So there are two plastics. One is transparent in nature, and another one is black in nature, which is absorbing and transferring. Both materials are absorbing. So this is a microscopic image of will be. So with the help of 8.3 watts and running at a velocity of 0.2 millimeter per second, we produced a beautiful well back over there. And it was conducted strength evaluation test. It is publication stage, so I want to completely discuss about all these things. So because of this facility available with our laboratory, we fabricated a micro Tesla valve with the help of this machine. The models have taken from this reference, and we fabricated the Tesla valve. This is a one-sided, which permit only in one direction. And this is another microfluidic chip we tested or we fabricated with the help of a micro laser cutting machine. By taking two input and one output, so that the idea is mixing of fluids happening in this region, so that it is highly useful in biomedical applications in microfluidic chips. The flow paths are engraved with the help of the same machine. So on the both the plates, there are two plates used. On both the plates, the engravement, we engrave the path, and then we close it together and weld it by means of the same machine. And this is a single input, double output. Since it is not being published, so I don't know much talk about this particular. And another important instrument we have here is a micron. With the help of this micro device, we measure the stiffness of both eye. It's also another publication stage. We don't want to talk much about this. You can see that, so this is a small probe which come and touch the surface of external surface of the eyeball, right? So by measuring or making a contact between these two surfaces, the necessary force will be produced, by which stiffness of eyeball is measured for a particular purpose. I'll show you the setup. So this is a micron instrument patented by my student. You see here. So this is the tip made of a polymer material. When it is touching the surface, it will produce a micro level displacement. Can you see it? Now, internally we have a mechanism. Also, the movement is observed by means of this microscope. So it will sense the data in the form of displacement, and then that will be produced as a output as a force, right? So thank you very much. I'm very much interested to be interact with the participants. Any doubt? I'm happy to interact with the participants.
Thank you so much, sir. Dear participants, if any of you having doubts or queries, kindly ask sir about them.
Thank you, Karthikeyan, for the comment.
Okay, sir, it seems no one is having doubts.
Whether I have presented very clearly or nothing has been translated.
No, sir, it was more informative.
Thank you.
Thank you, sir. Thank you for the very lively session. Thank you so much for being present here, and you have made it a lively session. It was not like a virtual session. Thank you. Thank you, sir.
Thank you very much. I have done well.
Yes, sir. Yes, sir.
Okay,
Yes, sir.
okay.
You can leave, sir.
Thank you very much for the opportunity given to meet all the young minds. Thank you once again to the Department of Electronics and Instrumentation for giving me this opportunity. Thank you.
Thank you so much, sir. Dear participants, we will have the second session by 11:30 a.m.
Hello, hello. 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 Hello, dear participants. Can you hear me?
Yes, ma'am, it's audible.
Uh, okay, sir. First, all of you bear with us. Actually, we have arranged one speaker from Tyagaraja College of Engineering. So he accepted our invitation. Suddenly, he got some other meeting like that. So that's why it's getting late. So please bear with us. Please wait for a few minutes.
Good morning to one and all present here. Uh, Now I am going to present the speaker of this session, Dr. S. Kavita, Assistant Professor, Department of Electronics and Instrumentation Engineering. She has completed his bachelor's and master's degree in Annamalai University and completed her PhD in the field of microelectronics and MEMS. She has a teaching experience of over 14 years and research experience of 10 years. She has completed relevant projects related to MEMS and structural health monitoring, and she has been she has published over 10 articles in reputed journals of international journals. Now I hand over the session to Dr. S. Kavita ma'am.
ஹலோ
சார்.
மேடம் வந்து ஸ்கிரீன் ஷேர் பண்ண சொல்லுப்பா.
ஓகே சார். Madam, you can share your screen, ma'am. Madam.
Hello, Sam. Hello.
Ma'am,
ஸ்கிரீன்
yes ma'am.
ஷேர் பண்ணுங்கப்பா.
Screen share பண்ணியாச்சு.
இங்க வரலையே.
Ma'am, it is not visible, ma'am.
ஷேர்
Not visible now. Wait.
ஷேர்னு இருக்கும் பாரு.
Yes.
Now it is visible, ma'am.
Now it is visible, no? Okay.
You can go for slideshow presentation. Ma'am, you can present your screen now, ma'am.
Huh? What?
You can go for the presentation mode, ma'am.
Yeah. I am not.
என்ன சார் அடுத்து எப்படி போய் அவங்க ஒய்ஃப் நடத்துறாங்க சார். அது ஒரு ஸ்பீக்கர் இப்ப 11 செகண்ட் வரலன்ட்டான். வாங்க வாங்க யார பாருங்க.
I'm facing some problem. Just wait for 10 minutes. Sam, now you can see my slides. Is it visible now?
Yes, ma'am.
Okay. So,
ஃபுல் விண்டோ போங்க. அது கீழே பாட்டம்ல இருக்குல்ல, அங்க மேல மேல அது
Ma'am, just select the presentation. Yes, yes, you are there. No, ma'am, you just select the presentation window that is present near the Google Chrome icon. Now you go for the slideshow, ma'am. That is near the screen minimizing. Yes, ma'am. You are now ready to go, ma'am.
okay, very good morning to all of you. Actually, as per schedule, the allotted session is in the afternoon only. So, unexpectedly, due to the speaker is not coming, just I'm going to present for you. And so before getting into this, first I would like to thank the organizing committee members and the scholars who are all working behind this program. So now actually I'm going to talk about development of MEMS accelerometer for structure health monitoring applications. I'm Kavita from A&I department. I'm working as an assistant professor. So actually my presentation covers motivation for this research, requirement of MEMS accelerometer for SHM application. Actually, for this presentation, I have considered 2 case studies. So the case study 1 covers MEMS piezoresistive accelerometer, and case study 2 covers MEMS comb dry capacitor accelerometer, and finally conclusions. So before getting into this presentation, first you should clearly understand what is SHM. Okay. So in order to get a clear understanding for this SHM, just I am comparing the SHM with the infrastructure system. Here, the doctor uses specialized equipment to check the patient's overall health, whereas in infrastructure system, the engineers utilize a specialized sensor to collect the information on the structure's overall health. Here, the doctor prescribes the medicine according to the patient condition. Whereas in infrastructure system, the sensors indicate the excessive stress or deformation on the structure. So according to the information is collected from the sensor, the engineer will take the necessary action according to the infrastructure health. So in preventive action can avert catastrophic consequences, early warning of the structural damage, improving the health of infrastructure systems. So one proverb is, we know that one proverb, prevention is better than cure. So in both the cases, the prevention is very important, whether it is human body or infrastructure systems. So for this, just I'm going to show the few examples. But before that, just I want to give the introduction about the SHM. Actually, the SHM involves the determination of structure health status of the concrete structures and potentially predicts the damage of the structure. Actually, the sustainability is very important, whether for both old and new buildings and bridges also. The structures deteriorate over time as they are continually exposed to harsh environmental conditions and continued or increasing loads. So the issue of aging infrastructure has gained increasing interest over the last decades due to few catastrophic failures. So now I'm going to show you the few examples for structure health monitoring. So what is structure health monitoring? Why it's very important to us? So those things and all you can understand from these examples, right? Okay. So the first figure shows the collapse of Kollidam Bridge. Okay, collapse of Perumal train tragedy. Actually, the island Kanyakumari Express derailed on Astamagi Lake near Perinadu, Kollam. In this incident, the Astamagi Lake the island express fell into Astamagi Lake. Okay, so in this incident, killing 105 people and 200 persons were seriously injured. Actually, this was the one of the major incident in the history of the Kerala state. And second figure shows the collapse of 8-story building which is located, this instance has happened in Mumbai. In this incident, 105 people killed and 150 get injured. And this figure shows the collapsed bridge of Mississippi River, which is located in USA. So in this incident, 13 people were killed and 144 getting injured. Okay. So actually, this Mississippi River bridge collapsed, subjected to heavy traffic and environmental loads over its lifespan. So causing deterioration and ultimately failure in under-design components. That under-design components are implemented under the design while construction is doing. Okay. So due to heavy traffic and environmental load, this bridge got collapsed. So from this example, what we can infer is the structure health monitoring of the bridges is very important. Okay. So in order to perform that, we need sensor. Then only we can perform the structure health monitoring effectively. Actually, there have been numerous collapsed bridges and buildings in India, but most of them which is typically related to illegally built structure or badly constructed. Suppose if you go to other country means, then you can find out most of the countries they have implemented structure health monitoring in most of the countries, but in India not that much implemented till now. Okay. Actually the essential technique behind this structure health monitoring is, suppose if you want to perform this structure health monitoring for any kind of bridge means, first the initial step is you should consider the span of the bridge. Okay. Suppose if the bridge, then according to the span bridge, you should divide that particular bridge into equal parts. Suppose if you divide the bridge span into 20 or 30 equal parts means, then you need 20 or 30 sensors. Okay. So according to the sensor span size, bridge span, you need the number of sensors. Okay. Suppose if you divide this 20 parts means in 20, you need 20 sensors. That 20 sensor acts as a slave sensors. Okay. So you need one master sensor or one reference sensors, because all the sensors, suppose if you are going to implement 20 sensor means you need one control or reference. Okay. So that control sensor or reference sensor you should consider as a mass. So from the different parts of the bridge, the slave sensor will capture the signal and send it to the master sensor or master accelerometer sensor. That master accelerometer sensor, what it will do is it will compare the signal, original signal with the capture signal from the slave sensor. So if there is any deviation, that deviation will send to the substation. So from the substation, we will come to know the status of the bridge. Okay. So now the technology is developed, right? So with the help of IoT and wireless wireless techniques, we can know the status of the structural state in our mobile phone also. Okay. Suppose if there is any deviation in any part of the bridge means, then automatically it will tell us in which part of the bridge getting deterioration like that. Then immediately what we can do is, so we can immediately inform to the higher authorities about the status of the health status of the bridge, and immediately we can stop the access of the bridge. So by this action, we can save a lot of things like a human life or infrastructure systems and so on. So this is the importance of the structure health monitoring. So few examples already I have discussed, right? So that so many tragedy also I have discussed, and few examples I have shown to you. So in order to avoid such a tragedy, the structure health monitoring is very important. As I mentioned earlier, to perform the structure health monitoring, the sensor plays an important role. So that sensor we should select properly. Okay. So nowadays, the conventional sensors and all are designed for high frequency application, but not that much efficient. That is not suitable for structure health monitoring application, because if you want to perform the concrete structure health monitoring or infrastructure structure health monitoring means it needs very low frequency sensor, right? But nowadays the commercial sensor and all designed for high frequency. So we have to design our own sensor, especially that is the exclusively for structure health monitoring applications. So that's why I have decided to design sensors, MEM sensors, especially for structure health monitoring applications. Okay, so now I'm going to discuss about the sensors especially designed for structure health monitoring applications, right? Okay, so now so as I mentioned earlier, for this presentation I have considered two case studies, right? One is capacitive and the other one is piezoresistive. So this slide, the following slides presents the conventional sensor they used for SHM, structure health monitoring application. Actually, the piezo, we know the concept of piezoelectricity. So the piezoelectricity is the ability of the crystal to generate the output voltage with respect to applied acceleration. Actually, it has three types of accelerometer: shear, fluxural, and compression accelerometer. So among this, the shear accelerometer is the predominant one because it's offered high frequency applications. Okay, so here you can refer that the shear accelerometer, the crystal is clamped between the outer mass and center post. So when acceleration is applied, the mass will create a stress or will cause a stress to excite a crystal that will generate the proportional output voltage with respect to applied acceleration. Okay, so the remaining two types of accelerometers like fluxural and compression accelerometer is not generally recommended because of suppose if there is any deviation in the base, that is easily transmitted to a crystal, so which in turn produce the output voltage, but that is not generally due to a applied acceleration. So that's why these two methods is not generally recommended. Only the shear accelerometer is only.
Sorry for the disturbance. Madam, please unmute
yeah.
your video.
Okay. Now it is okay?
Yes. Yes.
Okay. Okay. So now, as I mentioned earlier, so among this, the shear accelerometer is suitable for high frequency applications. Okay. So now, and now by moving on to the piezoresistive accelerometer, actually here we can see that the two strain gauges are attached to the fluxural, which is attached to the proof mass. Okay, so when acceleration is applied, what it will do is it will induce the strain on the fluxus, which is proportional to change in electrical resistance that we can measure easily. Of course, you can all of you can know the basic concept of the sensors. Okay, because most of them are familiar with the sensor. So this is for only the beginners only, because few participants they have applied from other department also. So that's why I have explained these things and all. Okay. Okay. So next one, the capacity sensor. It will sense the acceleration and change in capacitance with respect to applied acceleration. Actually, here the sensing elements are considered as two parallel plate capacitors. Two parallel plate capacitors connected in a differential mode as a differential capacitive transducers. Okay, so these two electroplates or access that forms a off-bridge differential capacitor. Okay, so now the next one is the servo force balance accelerometer. So till now, what we have discussed is all the accelerometer which is used to measure the deflection of proof mass or change in capacitance. But the servo force balance accelerometer is not like that. It's instead what it will do is actually in the servo force balance accelerometer. Here the inertial capacitor is there, that which is used to maintain the proof mass in the neutral positions. Okay, so here the peak voltage is detected by the detection circuit and which is fed to the feedback amplifier which is that reflects the so deflection amplifier. So from this we can measure the natural frequency. So next one is the electrical resistance strain gauge. Actually, with this setup, the strain gauge will deform. Here, the changes in the here the stresses developed in the gauge, and the area and length of the area is area and the cross sectional area of the wire is getting changed. That is directly proportional to the change in resistance. Next one, vibrating wire strain gauges. Here we can see that this vibrating wire, actually this is for high frequency, we can use this for high frequency application, or if you need better performance, then you go for vibrating wire strain gauge. Here this vibrating steel is fixed at both ends as shown in this figure. So here the electromagnetic in the figure you can see that the electromagnetic core is used to make a induction, which is used to induce this vibrating wire, which is directly proportional to the change in resistance. Okay, so next one, the last figure shows the vibrating wire strain gauge model. And now this figure shows the LVDT, that is a linear variable differential transformer. Actually here in this setup, the two, it consists of two coils. One is primary and another one is secondary. Here the AC voltage is applied in the primary, which induces the voltage in the secondary coil. So which is as the electromagnetic core moves, here the changing voltage in the secondary coil is directly proportional to the amount of voltage. Okay, so next one is the angular potentiometer. So in the angular potentiometer, it consists of a thin film resonator, which is connected with a movable wiper. That wiper in contact with the resistor. When acceleration is applied, this due to the rotation of this cable, it will make a deflection. So from the deflection, we can measure the deflection of this cable, that is directly proportional to the rotation of this coil. Next one is inertial based inclinometer. This it consists of a pendulous which is connected to the position sensor. Here this position sensor is used to detect the position of this proof mass. Okay, so now from the here the position sensor will produce a current, that current which is used to rotate this torque which is used to rotate this motor, that motor which is directly proportional to your output voltage. So now these slides presents MEMS accelerometers. So they are piezoresistive, lateral capacitive accelerometer, vertical capacitive accelerometer. And so already I have discussed a few macro or conventional accelerometers, except these resonant and fiber optic accelerometer. So in this resonance accelerometer, here we can see that the one end of this doubly clamped coil is attached with the proof mass, laterally movable proof mass. So when acceleration is applied, this will induce, the stress will be induced on the resonator. Okay, that is directly proportional to your nature frequency. Okay. The next one is fiber optic accelerometer. So here the first figure shows a side view, and second one is the top view of the fiber optic accelerometer. Here the shutter is placed between two electrodes here the shutter is coupled between input to output electrodes. Okay, so here the output is the amount of coupling is directly proportional to the shutter. Actually, under acceleration, the shutter moves either up or down. That is directly proportional to the coupling current. So by this, we can infer the we will note the value of the coupling current. And this slide presents the issues in conventional sensors used for SHM applications. So whatever the sensors, whatever the macro sensors we have discussed, so all are heavy, bulky, and handling is not easy. So more maintenance and expensive. So to overcome these difficulties, we can nowadays the recent developments in MEMS in sensor is the MEMS. Okay, so using MEMS technology, we can miniaturize any type of component. So these sensors are all tiny, high precision, low power consumption, fast response, reliable, low cost due to batch production process. So the motivation for this case studies are the first figure shows the traditional method SHM, and second one is the recent developments in SHM. So actually in traditional method SHM consists of a long wires. Suppose if there is any problem occur means then troubleshooting will be a major problem. So to avoid such a problem, we go for recent methods developed, that is MEMS technology. So nowadays the SHM implemented using this MEMS technology. So actually I have done a lot of literature studies. So in the literature studies, from that what I inferred is most of the researchers, they have used a commercial sensor for SHM applications. So Jerome et al. Have conducted extensive research on SHM. So most of them, which is they have obtained only a low sensitivity but high frequency, but that is not suitable for SHM application. Then Andres also reported the wireless MEMS piezoresistive accelerometer sensor for condition monitoring of AC motor. So he also obtained very low sensitivity but high frequency. So, however, little attention has been paid for the implementation of MEMS sensor with the intent of specifically addressing issues related to concrete SHM. And so this graph, from this graph, we can see that the first figure shows the commercial sensors. The first graph reports the commercial sensor used for SHM application. So this commercial sensor has low sensitivity, high noise floor. So just you can refer the first graph. It has low sensitivity and a high noise floor. But whereas the MEMS sensor used for SHM has high sensitivity and low noise floor, which is reported in the paper also. So from this we can conclude that no work has been reported on low frequency accelerometers, especially for concrete SHM applications. So that's why we have considered, we have designed low frequency accelerometer, low frequency and high performance accelerometer for SHM applications. So that is the main motivation of this case studies. So now you refer this slide. Actually, this slide in this table presents a few conventional accelerometers listed over here. And last one is the journal paper, which is reported by Jerome. Actually, here this table you refer that all the quartz accelerometer has low sensitivity, high frequency, high resonance frequency, low noise flow, high noise flow, and low resolutions. For example, you can consider this Freescale semiconductor. It has low sensitivity in the range of millivolt per G and high natural frequency, that is 1000 hertz. But 1000 hertz is very high for high frequency for SHM application, and high resonance frequency, high noise flow around 350 micro G per root hertz, and low resolution around 620 micro G. So that is, which is completely not suitable for concrete SHM application or any infrastructure application like a bridge or any type of building like that. Okay. So, and Jerome also reported that he has conducted so many research and reported that the sensitivity is 1.25 millivolt per G and frequency is 680, and high resonance frequency is 680 hertz, and low noise, high noise floor 20, and resolution is also high. So from this, what we inferred is the sensitivity is inversely proportional to your frequency. If the sensitivity is more, then frequency is low. This is a simple concept. So based on this concept, we have developed our own sensor. So, and it has larger resonance frequency, will have lower sensitivity. The cord sensor designed for high frequency application, and it has high noise floor and low sensitivity. So these are the important factors we should consider while designing the accelerometer, especially for structure health monitoring, concrete structure health monitoring application. So based on these factors, we have designed our own sensor. That is, we have designed low frequency, low G, but high performance sensors. Okay, so now we can see that this slide presents few essential characteristics of MEMS accelerometer for SHM application. It needs high sensitivity with ultra low noise floor, since most ambient vibration in concrete structures are characterized by low amplitude acceleration. It should have smaller bandwidth, since concrete structures have smaller natural frequency, and it should have
Sorry for the interruption, ma'am. Your voice was not audible, ma'am. Hello? Dear participants, kindly wait for some time.
Hello.
Sir, yes, sir.
Hello, is it audible?
Ma'am, yes, ma'am. It is audible, ma'am.
Okay, Sam, we will continue. Shall we continue in the afternoon session? The remaining things.
Yes, ma'am. We can inform the participants, ma'am.
Yeah. So
Participants, the session will be continued in the afternoon. Thank you, ma'am. Thank you for presenting the case studies
Sir,
on
time,
your.
sir. What is the time, starting time? 2 o'clock?
at 2 o'clock.
Just
Two
a minute.
o'clock you can start.
Okay, ma'am. Thank you.
Okay.
Thank you for the wonderful session, ma'am. We'll meet participants. Will meet at the afternoon session by 2 p.m. Thank you.
Hello? Hello, participants? நான் என்ன பார்த்து சுத்தமாவே கேட்கல சார் சொல்றாரு எனக்கு நெட் விட்டு விட்டு வந்தது அது சுத்தமா வந்துச்சா இல்லையா சொன்னாங்க கால் பண்ணி பட் எனக்கு வந்து நான் ஸ்க்ரீன் என்டையர் ஸ்க்ரீன் இருக்கிறதுனால என்னால பார்க்க முடியல அதனால எனக்கு தெரியல இப்போ என்ன சுத்தமா இருந்துச்சா ஆமா இப்போ என்னாச்சு இப்போ எதுவுமே வரலையா சுத்தமாவே எதுவுமே வரலையா கடைசியிலன்னா இல்லையா ஃபர்ஸ்ட்லாம் வந்துச்சு அதாவது அப்படியே கட் ஆயிடுச்சா ஆமா ஆமா அதுக்கப்புறம் வரலையா அது வரையும் வந்துட்டு இருந்துச்சா சரி என்னப்பா என்ன இது ஆரம்பிச்ச டைமே சரியில்லைன்னு தெரியல எனக்கு நெட் வர ப்ராப்ளம் இங்க வர வீட்டுல துட்டு வருது மூலம் வர வெளியில வருது ஆனா உங்க இதுலாம் கரெக்டா நடந்துச்சேப்பா இது என்ன தெரியுமா இந்த மாதிரி பண்ணி நம்ம டென்ஷன் ஆகி விட்டான் நானே வந்து மதியானம் பார்க்கலாம்னு நினைச்சிட்டு நான் உட்காந்துருந்தேன் ஏன்னா எனக்கு டைம் இல்ல மதியம் 1 hour டைம் இருக்கும் பார்க்கலான்ட்டு அவன் ஏதோ மீட்டிங் ஏசி டிப் பண்ணிட்டாங்க சாரி மேடம் ஐயோ நான் எல்லாம் மறந்துட்டேன் நான் என்னத்த சொல்றது அது எனக்கு இன்டிமேட் பண்ணா நான் ப்ரிப்பேர்டா இருந்திருப்பேன் நான் ஃபோன் பண்ணி 11:40 ஃபோன் பண்றேன் ஐயோ சாரி மேடம் நான் டக்குன்னு அதுக்கப்புறம் நான் கடையில இருந்தேன் நான் அதெல்லாம் அதை இது பண்ணி விட்டு கடைக்கு வந்தா அப்புறம் அங்கேயிருந்து முடியாத நான் ஆன் பண்ணுறதுக்கு எனக்கு நான் என்ன பண்ணுறதுன்னு தெரியல டென்ஷன் ஆயிடுச்சு டென்ஷன்ல எது பண்ணாலுமே கொடுக்க மாட்டேங்குது ஏன்னா அசிங்கமாயிடும்ல பார்ட்டிசிபென்ட்ஸ்க்கு என்ன சரி ஓகே நான் உடனே லாகின் பண்ணிடுவேன் ஸோ அதுலேருந்து கண்டினியூ பண்ணுமா இப்போ ஏதாவது ஸ்டூடெண்ட்ஸ் ஏதாவது இன்ட்ராக்ட் பண்ணாங்களா இப்படி ஃபர்ஸ்ட் செஷன்ல அப்ப ஆன் பண்ணி வச்சுட்டு போயிட்டாங்களா இல்ல ஒன்னோட கொஞ்சம் எஃபெக்டிவா அந்த மாதிரி இருந்துச்சுப்பா உங்களுக்கு பசங்க நல்லா கேட்டாங்க இல்ல இதையும் தாண்டி இன்னொன்று வந்து ஆமா இது வந்து இந்த ஃபீல்டு கொஞ்சம் ரேர் தான் அவன் சர்டிஃபிகேட் வேலை அட்டன் பண்ணுறான் ப்ளஸ் வந்து அவன் பிரைவேட் காலேஜ்ல ஒர்க் பண்றானா அதனால சும்மா சர்டிஃபிகேட் ஏதோ ஒரு காரியம் பண்ணிட்டு அவன் போயிடுறான் இதெல்லாம் நடக்குது சரி
Sam? 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 Hello? Indela?
Hello. Audio கேக்குதா? Translate. Go on. எதுக்கு பக்கம் வெளியே போறேன் நான் என்ன பண்ணுவேன்
கேக்குதா?
ஆடியோ ஓகே.
சரி சரி நீ கட்டணும்.
வீடியோ அதோட நல்லா இருக்கு. இது ஃபேவரட் பண்ணிக்கலாம்.
Ma'am, can you hear me, ma'am?
Hello. Hello, Sam. Hello.
Ma'am? Yes, ma'am.
Yeah, I'm hearing your voice.
Ma'am, just a minute. Yes. Am I audible, ma'am?
Yeah. It's audible only.
Okay, ma'am.
At what time we should start the session? 2 o'clock, shall we
2, ma'am.
start?
2 to 3:30.
2 o'clock.
Yes.
Okay. So 2 o'clock we will start it.
Okay. Ma'am, can you just go with the slides, ma'am?
Hmm. Now it is okay?
Yes, ma'am.
Okay. So 2 o'clock we will start it.
Okay, ma'am.
So 10 minutes is there. No?
Okay. Ma'am, can we start, ma'am? Ma'am?
Hello?
Ma'am, can we start, ma'am?
Yeah, sure. We can start.
Okay. Good afternoon, all present here. The third session of day 1 is to be addressed by Dr. S. Kavita. She is an assistant professor in the Department of Electronics and Instrumentation Engineering. She has completed her bachelor's degree in the field of Electronics and Instrumentation Engineering and master's in the field of Process Control and Instrumentation Engineering. She has completed her PhD in the field of microelectronics and MEMS. She has a teaching experience of 14 years and research experience which consists of 10 years. She has published more than 15 articles in reputed journals, and she has been working in the field through R&D projects which are worth of around 66 lakhs. And now she is going to present on the case studies on MEMS sensors for bridge structural health monitoring applications. Ma'am, the session is yours.
Thank you, Sam. Hello, Sam. How is it visible?
Ma'am, yes, ma'am, it
Can
is
you see
visible,
the
ma'am.
slides? Okay.
The slides are good, ma'am.
Okay. So, dear participants, good afternoon to all. The morning section, actually, due to some technical issues, it's not completed fully. So first, so sorry for that. So now the title will be continued now. I think in the morning section, I have stopped with this slide, I think so. Okay, so the morning, what we have discussed is actually for structure health monitoring application, we are going to design the sensors, right? So in the morning we have discussed like what is structure health monitoring, what is the necessity of doing the structure health monitoring continuously, then which one plays an important role for structure health monitoring, then why we go for sensor, then what type of sensors we have to select it. So then what are the which types of sensors and what are the key factors you have to consider while designing the sensors. So those things and all in the morning sessions I have discussed, right? Okay. So now the advantage these things actually in the morning I have discussed. I don't know exactly whether you can see I have presented or not, because due to issues I'm not sure whether I have presented this one or not. But anyway, so these things and all already you know this, the design and analysis, the piezoresistive mechanism and Wheatstone bridge concept and all already you know this. Then advantages of MEMS, it's these things are actually I am taking only the basic things, right? Okay, so the advantages of MEMS are it's used in vital application. It's a very small size, mass, volume, and it consumes low cost, low power consumptions, and it's a small thermoconstant and so on. Then application, it's used in vital application, but for example, I have listed only a few. It's used in automotive application like airbag system, vehicle security, then interior brake lights, automatic door locks, and so on. And it's used in consumer domain also, like appliances, sports training devices, computer peripherals, car and personal navigation devices, active subwoofers, and so on. And multi-purpose also, the MEMS are used in tanks, planes, then equipment for soldiers. Okay, so these are all the few applications on MEMS actually. So now in the morning, as I mentioned earlier in this presentation, I have concentrated only 2 case studies. So the case study 1 covers bulk microemission piezoelectric MEMS accelerometer. The case study 2 covers surface microemission capacity accelerometer, right? So why we have chosen these 2, especially this MEMS piezoelectric and MEMS capacity accelerometer for structure health application, structure health monitoring application, and all already discussed in the morning section. Okay, so now first I am moving on to the case study 1, that is bulk microemission piezoelectric MEMS accelerometer. Suppose if you want to design any kind of sensor, not only accelerometer, any kind of sensor for some other application, means first you should consider the specifications, right? So what are the specifications for which kind of application you are going to implement your sensor? For example, it depends on the specification only, it depends on the application only, you can fix the specification of any kind of sensor. For example, if I want to design my own sensor for SHM application, means then what are the specifications you need? In the morning session I told you, for SHM application the sensor should have high sensitivity and low frequency. So that is very, very important factor. So these are all the requirement. So according to the requirement, you have to fix the specifications, right? So now I have fixed the specification as shown in the table: the acceleration range, resonance frequency, voltage sensitivity, cross-axis sensitivity, noise floor, resolution, and overload protection. So these are all the important key factors for you have to consider for designing the accelerometer. Okay, so now here I fixed the acceleration range 0 to 2G, and resonance frequency you can see that 100 Hertz only, because this is because I'm designing my sensor for low frequency application. So that's why I fixed the natural frequency as 100 Hertz, and voltage sensitivity is 25 millivolt per G per volt. Okay, so these two are very, very important factors you should consider while designing the accelerometers. Okay, so now I fixed the specification. This is the initial steps. So next what you have to do is, based on the specification, you have to optimize your parameters, right? So now what is our aim? I have to design a MEMS piezoelectric accelerometer. So I have the specification. So based on the specification, we have to create the structure. So in order to create the structure, you need some parameters, right? You have to optimize the parameter. So I have optimized the parameters, like this is the optimized parameter. So the second step is I had optimized the parameter. Then based on this optimized parameters according to the specification, then I have created the structure in simulation software. I have adapted IntelliSuite as well as Contest software. So you can you can adapt any kind of simulation software for creating the structure. Okay, so now based on this optimized parameters, I have created the structure like this. Okay, so now here you can see that the first one is a cross-sectional view. So already few few of you are familiar with the MEMS area. So this is what is a cross. So what about the cross-sectional area? So what about the top view? Then these things and all already you know that the cross-sectional area. The first one shows a cross-sectional area, and second one is a top view, and third one is 3D view structure. That's why I have created in Coventera software. And here actually in this slide the deflection formula I have presented. So using this deflection formula only, I have applied the deflection of this proof mass. So the basic concept, of course, in the morning I have discussed with you. While applying the acceleration, the proof mass moves up and down, right? So using this deflection formula, I have applied the deflection for this MEMS piezoelectric accelerometer. So in this formula, n is the number and m is mass, g is the acceleration, l is the length of a beam. Okay, l is the length of the flexural beam, and e is the Young's modulus that you know, and I is the moment of inertia. So those parameters and all you have to give it all a constant. Only you have to change the acceleration and flexural length. Okay, so using this formula, you can obtain the deflection sensitivity of the fluid mass. So next, I'm going to show you the fabrication. What are the fabrication steps involving with the piezoresistive accelerometer? Okay, so first I have taken the silicon substrate. Then I have deposited SiO2 above the silicon substrate. Then I have deposited polysilicon layer above the oxide layer. Okay, then I have etched these portions in order to get the piezoresistor fluxes and piezoresistors. Okay, with the help of some fabrication techniques. The fabrication techniques is a different issue. Okay, so with the help of the pattern transfer and after pattern transfer, etching and removing and all, I have obtained these kind of structures. So here this red one indicating the piezoresistors. Okay, then I have removed these portions in order to get the anchor from the bottom edge, using the bottom edge that we can do from the bottom of the silicon substrates, right? So these are all the steps involving with the MEMS piezoresistor accelerometers. So now, so the same thing. Here, these are the process steps. They're showing the process steps. So what are the process steps I have taken for? I have created for MEMS piezoresistor accelerometer. The first one is silicon substrate. Then deposition of silicon oxide layer for 1 micrometer thickness. Then I have performed the silicon etch. From the bottom edge, from the back side to get the proof mass and suspension beam. Then I have deposited the polysilicon layer above the oxide in order to get the piezoresistor. Then I have finally I have etched the remaining portions in order to get these structures. Okay. Now this is my final structure. So this structure only I have created in IntelliSuite as well as Coventera software. And this structure I have created in Coventera software. So the first one, then after the structure is created, I have performed so many analysis. Okay, so because you have to confirm whether your created structure is performing well or not. So that's why I have done so many analysis on the created structure. The first one shows the model analysis. So using this model analysis, I have extracted the natural frequency, right? So here we can see that the middle one is the proof mass. It consists of four fluxes, okay, the suspension beam, and the outer, the blue color indicating your the frame. Okay, so now that is your substrate. Okay, so now actually here what I have done is just I have applied the acceleration. Then according to I have extracted the natural frequency from this analysis. Here I got the natural frequency 103 hertz. It's approximately 103 hertz. Actually, this frequency is matching our frequency what I have specified in the specification. The specification already I told you, first in order to design the sensor, first initial step you have to design the specification. Actually, I fixed this natural frequency is 100 hertz. Okay, so the same 100 hertz I obtained through the simulation. That is it's around 103 hertz, which just closely matches with your theoretical value. Then I have done the mode 2 analysis, and then mode 3. Actually, and the Coventera, the mode 1, mode 2, and mode 3 both analysis you should get the same frequency. Okay, so now I have listed these values. I have listed all the what are the values I got through simulation. I presented in the table. So here you can see that the mode 1, the theoretical mode 1 frequency is 101, and Coventera the simulation value is 103. So all the values are closely matches. All simulation values are closely matches with the theoretical value. So next, actually so many analysis I have done only. I have extracted only the natural frequency also. So you can perform, I have done deflection analysis, capacity analysis, then the stress analysis. Okay, so many analysis I have done based on that created piezoresistor accelerometer structures. Okay, so next I move on to the case study 2. In the case study 2, the surface it describes the surface microemission folded beam capacity accelerometer. So here Actually, this is a structure. The first one shows a capacitor accelerometer structure. The middle one is the proof mass. It consists of the combs. It's the electrodes and all is looking like comb shape. That's why it's called a cone drive capacitor accelerometer. So here, so the outer one, that pink color one indicating the anchors. Okay, the anchor is attached with the your comb drive. That is electrodes. So all the electrodes are movable electrodes are attached with the proof mass. Here the one electrode is fixed and the other one is attached with the proof mass. It forms a capacitor actually. It forms a capacitor. Here you can see this. This is the equivalent structure of the capacitor accelerometer. Just to refer the top one, the equivalent structure. The middle one indicating the mass. Here the A and B denotes the electrodes. Okay. So here you can measure the capacitor C1 and in between that is nearer to B, you can measure the capacitor C2. So these are the formulas I have adapted for this capacitor accelerometer sensor C1, C2 and C, the deflection B, C is your change in capacitance, del C. Okay, so if C1 minus C2 is a del C. So these are the formulas I have adapted for capacitive home drive capacitor accelerometer structure. So now, so what I told you here, the same specification I have taken for capacitor accelerometer also, because the specification is same thing, because both accelerometer, both sensors I have designed for same application. So that's why my specification is same thing. Only according to the structure, only the optimized parameter is getting changed. Okay, so now this is the optimized parameter. This table shows the optimized parameters for home drive capacitor accelerometers. So you have to optimize the parameters like what is the beam length, the beam width, mass width, movable finger length, and movable finger width, and fixed finger length. Then how many fingers you are going to implement. Okay, so these fingers and all, it depends on your specification only. Okay, so according to your specification, you should optimize the parameter. Then these are the optimized parameters, and based on the optimized parameters, I have created the structure like this. Okay, actually here you can see that here the number of fingers are. So this is the comb fingers. Okay, actually the first three fingers called one unit cell. One unit cell, middle one is mobile, and two the pink color, the anchor is attached to no. So that two are fixed plate. This is similar to capacitive only. The middle one is mobile, and the first and last one shows you that indicates your fixed fingers. Okay, so actually it forms a capacitance. The first gap forms C1 and second gap form the capacitance C2. So from this we can extract the change in capacitance. And this slide presents fabrication steps involving in capacitive home drive capacitor accelerometer. The first one we have discussed now, that fabrication step is for piezoelectric MEMS accelerometer, and this is the fabrication steps I have created for home drive capacitor accelerometer. So first I have taken the silicon surface. Actually, this is just you refer the figure G. So this is our final structure. So according to this final structure, we will develop the process steps, right? So first I have taken the silicon substrate, then deposit silicon nitride in order to, this acts as an insulation layer. For 1 micrometer thickness, I have deposited above this silicon substrate. Then I have deposited PSG layer. Actually, this acts as a sacrificial layer because we have to create the damping. No, for capacitive accelerometer, we need damping. So in order to create that, I am depositing I have taken the sacrificial layer, BSH sacrificial layer. Then pattern transfer, mask is preferred. Then I did the pattern transfer. So after all these steps are getting over, then I got the structure like figure D. Then I have deposited the polysilicon above this PSG layer. That is just you refer the figure number E. That brown color, maroon color indicating this polysilicon layer. Actually, this is called the structural layer. Okay, this is called structural layer. So now, actually, I need a comb kind of structures I need. So in order to get the comb kind of structure, so I have to prepare the mask, then you have to do the pattern transfer, then etching and all, and finally you can get the structure as shown in figure G. Okay, so this is my final structure. So these are the fabrication steps involving with the accelerometer. Then I have done the model analysis for capacity accelerometer structure also. So here, this is a structure I have created in IntelliSuite software. So that one I have done in both the simulation software, both IntelliSuite as well as Commenter. And for this home drive capacitor accelerometer also I have done both in both softwares. Okay. Actually, this is I have done the whatever I have presented here. This one I have done through IntelliSuite software. So I extracted the frequency 97. You can refer the figure 97. So this practical simulation frequencies matches our theoretical frequency 100 Hertz. So next I have present the this slide. I have presented the deflection analysis. Actually here the deflection analysis I have compared for both the piezoresistor and capacitor accelerometer. Actually how I presented in this presentation is first the model analysis for sensor 1 and sensor 2, that is home drive and piezoresistor accelerometer I have presented separately. And this one and all I have make it in I made it in the same slide. Okay, the deflection analysis I made it for both piezoresistor and capacitor sensor. So here actually what I have in order to perform this analysis, what I have done is in the created structure just I applied acceleration, then I have extracted the deflection from the proof mass. Actually, on that slide I showed already had discussed with it the deflection one formula I already I have in that slide I have presented. So using that formula I have extracted the deflection. Then after that I have made the graph is plotted like this. So here the graph is plotted for deflection versus acceleration. So here we can see that the acceleration is if the acceleration is varying, the deflection is also varying. So here I cannot here both are linearly that is the acceleration versus here I'm getting the linear curve for acceleration versus deflection. So this is actually I have made the graph for both simulation as well as theoretical. So all are here you can see that all are closely matches with the practical value. Okay. Actually, my acceleration range is 2g. So up to 2g, I keep on varying the acceleration from 0.1 to 2g. Then according to that, I have noted the deflection range. Then finally, I have made the graph like this. Okay. And this is also confirm. Actually, this analysis also confirm our observation. So here the theoretical frequency matches with the simulation value. Then I have done cross-axis sensitivity analysis. The cross-axis sensitivity analysis, the first one is the piezoresistor accelerometer. That is for single axis. Single axis already, I think you're familiar with the single axis, dual axis, and triaxial accelerometer and all. So single axis accelerometer means it will sense acceleration in only one axis. Dual axis means it will sense acceleration in two axes, whether x and y axis like that. And tri-axis means in all three axes it will sense the acceleration. Okay, so if you want to design the sensor means this analysis is very, very essential. The cross-axis sensitivity analysis, because you should clear whether our design sensor is it's acting whether it's a single axis or it's performed whether in single axis, dual or triaxial. So the first figure shows the cross-axis sensitivity analysis of piezoresistor accelerometer. So here we can see that here the acceleration is varied, then corresponding deflection is measured as shown in the figure. Then after that finally I have made the graph like this. So here also while acceleration is varied, this deflection is also varied. So here also I am getting the linear graph. Okay, linear graph, and apart from this the theoretical values are closely matches with your simulation value. So here we can see that the x and the z axis are coincident. Here only the z-axis deflection is higher, is comparatively x and y-axis. Here the x and y-axis are negligible as compared with the z-axis. So from this, what we can conclude is this piezoresistor accelerometer. It's a suitable for single axis accelerometer because it sends the acceleration in only one axis. So I got acceleration in only z-axis only. Other two axes are negligible. Okay, from this graph you can see it. And the next one, the cross-axis sensitivity analysis for capacitor accelerometer. So this analysis I have done it for capacitor accelerometer also. The procedure is same thing. The acceleration is applied. I keep on getting the acceleration. Just I noted the deflection for the creator structure. Then finally you can I make the graph. I have made the graph like this. So here you can see that the acceleration. I got the acceleration in x and y axis. Okay, x and y axis, that z axis, sorry, x and x and z axis, and y axis acceleration is negligible. So the acceleration is sensed in both axes, both dual axis. One axis is negligible. So from this, we can conclude that this capacitor accelerometer is dual axis accelerometer because it sends acceleration in dual axis, two axis. Okay, the other axis, the third axis is negligible. So it's evident from that these results that the main axis sensitivity is high is compared with the other axis sensitivity, thus demonstrating the ability to this structure to reduce the cross-axis sensitivity. So the x and y axis sensitivities are 0.7% and 0.6% of main axis sensitivity respectively. And so next I have done the voltage sensitivity analysis of piezoresistive accelerometer. So I mentioned in the earlier slides. Actually, I have done the piezoresistive accelerometer. I have created that piezoresistor forms a Wheatstone bridge, right? That and all already we know this. In piezoresistive that setup, suppose if you are implementing the 4 resistance means the 2 resistors will increase and other 2 resistors will decrease. So that and all basic concept already we know that. So actually, this analysis I have done to confirm that observation. Just I have done this analysis. Here the resistors are just you refer the Wheatstone bridge. Here the resistors are placed such that here the R1 and R3 increase and R2 and R2 will decrease. And that means R1 and R3 experience a longitudinal stress, and the R1 and R3 will that will increase. The opposite resistors R2 and R4 it experience the transverse stress. That means these two resistors will decrease. Okay. So then here also the acceleration is applied. I have extracted the voltage from this voltage from that. Then from that I have extracted the change in voltage. With that formula already we know that the Wheatstone voltage formula. So for using that formula, I have extracted the change in voltage. Then after that, I have made the graph like this. Okay, so here we can see that the first graph shows actually this is called stress analysis. The first you can refer it just the proof mass nearer to proof mass. So here we get that red color one indicating the maximum stress. So maximum stress I can get the maximum stress nearer to the proof mass. So here you can see that, and this is for the first one. Okay, the R1 and R2 and R2 and R4. Here the stress is decreased. Here the stress is increased. Okay, so you refer the graph. You can observe that the R1 and R3 the tensile longitudinal stress is increasing. So here the stress is increasing, whereas here the stress is decreasing. Okay. Next, the voltage analysis of capacitor accelerometer. So actually, this forms the differential capacitor bridge. Okay. So using this formula, I have extracted the voltage sensitivity analysis of capacitor accelerometer. So the voltage sensitivity analysis is expressed as Vs equal to del C by 2 C naught into Vm. Vm is a modulation voltage. This is 1. Del C is a change in voltage. Okay, C naught is the rest capacitance. The capacitance is at rest. So without applied any acceleration, it won't change. The proof mass not getting, it's not moved. So that is called C naught, that rest capacitance. So using this formula, I have extracted the sensitivity, voltage sensitivity. So the voltage using this formula, I have estimated the voltage sensitivity is 24 millivolt per G per volt. Actually, here you can notice that initially in the specification I have fixed the same frequency. Okay, so now I have obtained the same frequency through the simulation. So this analysis also confirms our observation. So next one, I move on to the noise analysis. Noise analysis of MEMS piezoresistive accelerometer. Actually, if you're designing the accelerometer, the noise analysis is very, very important. Okay, so you should perform the noise analysis. Then only we can conclude. We will come to any conclusion, because the noise is very, very important. We have to reduce the noise in the sensor. Okay, then only it will be performing well. So the noise is very important factor while designing the accelerometer. It is the noise in the piezoresistive accelerometer equal to the Johnson noise plus thermomechanical noise. So these two noise are normally occurring in accelerometer. Johnson noise and thermomechanical noise. So these two noises we have calculated. So all the mathematical formula I have presented in my paper. What is the formula we have adapted for Johnson noise, and what is for the formula for thermomechanical noise. So those things and all I have presented in my paper. You can refer it. So Johnson noise and thermomechanical noise I have calculated using this formula, and from this I have obtained the total noise in the piezoelectric accelerometer. Okay, so the VNT is the total noise equal to Vj plus XTM square. Vj means Vj represents a Johnson noise, and the XTM is represents a thermomechanical noise. So I have calculated separately, and finally from this I have obtained what is the Johnson noise. Okay, so the Johnson noise is denoted by VNT. Then after obtained actually using this formula, I have obtained the total noise in the accelerometer is 4.53 micro-G per rotance. Okay, so here also the noise is reduced. But in the morning I have discussed that quartz accelerometer and all has a high noise flow. It's approximately 200 or 30, 20 like that. So that and all completely not suitable for structure health monitoring application. So now I have designed. I have extracted the I have extracted the noise. I have estimated the noise for my designed piezoelectric accelerometer is 4.53 micro-G per root hertz. So this is comparatively low as compared with other quartz means that is commercial accelerometers. The resolution of piezoelectric accelerometer can be written as R equal to VNT by SV. SV means SV represents the voltage sensitivity and VNT is the total noise. So the total noise how we have obtained? The total noise is obtained from Johnson noise plus thermomechanical noise. So using this formula, we have obtained the resolutions of the piezoelectric accelerometer. So resolution also I have estimated as 12.72 micro-G. So this is also very low as compared with commercial sensors, commercial accelerometer, and one paper already I have shown you that Jerome. So that Jerome he conducted the same the structure health monitoring using the commercial sensor, but they have obtained high resolution. It's around 20 or 30 like that. Sorry, 30 like that, 30 micro-G. Now the resolution is also is increased. Okay, so now next one. The thermal noise displacement for a damped capacity. So that is a noise formula for means piezoelectric accelerometer I have adapted for case study 1, and for case study 2, that is for means capacity accelerometer, I have adapted this formula. So the thermal noise, the displacement for a damped capacity accelerometer outside the resonance F0 is given by XF, modulus of X of F equal to root of 4 kBT by omega naught squared ms into Q. Okay, so here in this formula, the Kb is a Boltzmann constant, T temperature, whatever temperature you are having, you are maintaining, and omega naught resonance frequency, ms is the damping that mass, and Q is the cost factor. So these things and all you should calculate, and from that you can easily obtain what is the thermal noise of the capacitor accelerometer. So the unit for this thermal noise is meter per root hertz. Okay, so then from this I can easily obtain the noise flow. So noise flow is represented as Gn. So this is a Gn is represented noise flow. So the noise flow equal to modulus of Xn of F, that is thermal noise, divided by Sd. Sd is a deflection sensitivity. Sd means deflection sensitivity. So the deflection sensitivity already, how we can obtain the deflection sensitivity? Actually, we have to apply the acceleration, keep on applying the acceleration. We have to vary the acceleration. So according to that, you should note down the deflection sensitive deflection, and from that deflection you can obtain the deflection sensitivity. Okay, for 2G. So per 2G or per 1G like that. So this is for deflection sensitivity per G. So per G I have obtained 1.755 micro-G per 2 times. Okay, this is also very low. So I have reduced the noise also. Is comparatively I got a very low noise flow is compared with the commercial sensors. Okay, so this also so this analysis also confirms our observation, and now I compare the performance of present sensors with quartz accelerometer sensors. Okay, so now the present sensors already in the morning session I have listed few commercial sensors, right? that is analog devices, free-scale semiconductor, and one paper also I have quoted, genome paper. So these and all, just you compare these commercial sensor values with your piezoresistive accelerometer, that is case study 1 and case study 2. Okay, so what are the parameters I have obtained through MEMS piezoresistive and capacity accelerometer? I have compared with the commercial sensors. So here we can notice that in piezoresistive accelerometer, that is case study 1, I have obtained the frequency 100 Hz. 100 Hz, this is very, very low is compared with commercial sensor. Just you refer that column. And sensitivity also I got 4. In the piezoresistive accelerometer, I got 4 millivolt per G. So this is also high because our aim is, our goal is we have to improve the, we have to increase the sensitivity, right? So for the sensitivity is 4 I have obtained for piezoresistive accelerometer, and natural frequency 100 Hz and resonant frequency is 100 Hz, and noise floor is very low, 4.53. The 4.53 is compared with other commercial sensors, and resolution is 12.72. So the resolution is also okay. I have obtained the good resolution. And next one is the capacity accelerometer, that is case study 2. Just you compare the capacity accelerometer with piezoresistive and commercial sensors. So now in the case 2, that is capacity accelerometer, I obtained the frequency, deflection 24 millivolt per G. And natural frequency is 100, and resonant frequency is 100, and noise floor is 1.12. So this is very, very good as compared with piezoresistive accelerometer, that is I have done in case study 1, and commercial sensors also. So, and likewise the resolution also I got good resolution is compared with other quartz accelerometer and case study 1. So from this table, what I conclude is the capacity accelerometer among actually I have adapted both piezoresistive and capacity accelerometer, right? So from these two analysis, what I conclude is this capacity accelerometer sensor is a predominant one. You can use it for this is exclusively used for structural health monitoring applications. Okay, because this capacity accelerometer, this proves our earlier observation. So whatever the values I have fixed in the specification, the same value I got through the simulation for both the capacity and piezoresistive accelerometer. While comparing the case study 1 and case study 2, so what I conclude is the MEMS capacitive accelerometer sensor is suitable for structural health monitoring applications. Okay, so now this works attempts to design a MEMS accelerometer exclusively meant for concrete SHM application. The comparison results clearly bring out the superior performance of MEMS, home capacity accelerometer, and piezoresistive accelerometer designed in this work is compared with quartz accelerometers. Okay, then piezoresistive accelerometers have good high frequency performance than capacity accelerometer, but concrete SHM needs superior performance at low frequency. Displacement sensitivity of piezoresistive and capacitive accelerometers are considerably higher than the values reported in the literature, thus justifying the need to exclusively design and fabricate accelerometer for SHM and seismic applications. And this structure, actually, this figure shows a photovoltaic cell. Actually, we have this is the schematic of PN junction solar cell. Actually, this one we have fabricated through Indian Institute of Science. Okay, the mask we have created. Then we went. Then we go for. We have done the fabrication also. Okay, so this is a mask patterns we have. We got through EIC Bangalore. Okay, so using this, so after this is the pattern for PV cell. From this device, we have achieved the good voltage, better voltage as compared with other photovoltaic cells. Okay, so this one we have fabricated in IIC Bangalore. So these are all the references. Thank you. So any doubts regarding this? Participants, you can ask your queries. Participants, you can raise your queries. My presentation is over. Actually, one of the participants, her name is Vishalachi Ramasamy. He has raised the question: how do we can do the fabrication? Actually, suppose if you want to go for fabrication, means first you should create the process steps. Okay. Then after once your process steps, once you confirm with the process step, then what you have to do is you have to meet the concerned person. Suppose if you want to do the fabrication with IIT or IAC or some other IIT, means because the fabrication facilities are available in IIT Chennai or in IITs, all IITs. So if you want to perform the fabrication, means then you first you create the process steps, then you should meet the concerned persons, that the experts, who are the experts available in the concerned institution. You have to meet that person, then you should get the concurrence confirmation from that particular person. Okay, then you have to create the mask and so many things. Then after that only they will be approved for doing the fabrication.
Ma'am, can you hear me, ma'am?
Yeah.
Myself, Radeep, ma'am. I'm attending this FDP. I have one small question, ma'am, regarding fabrication only. Do we have any government authorized any fabrication easy facilities available, something like that? Whether any national this MEMS program under that,
Actually,
any
the
scheme is
national.
available?
No, but INEP, yeah, INEP, that one scheme is available in IAC, Indian Institute of Science. Actually, you have to submit the proposal. So based on the proposal, they are calling for making the presentation. Once they are satisfied, then you can do the fabrication. You can
Okay, ma'am.
upload
So,
the INEP Science through just you refer the INEP portal, you can get the information.
oh, okay, ma'am. Ma'am, one more doubt: whether if we design this in Intel suite, or whether the GDS2, that final file which is being generated, whether the same thing is, whether the same file is usable in the fab point also, or whether we have to convert it
Same
to something.
file. Yeah. The same file you can't use it, but this you can. What you can do is once you create the structure, just the simulation and all for confirming your device is working or not only. Suppose if you want to go for fabrication, means then you have to create a mask, your own mask. That is, so many softwares are available, Clevin and L-Edit. You refer that, so that using just you have to adapt that software, you have to make a mask pattern. So how many, what is your wafer size, how many device you can accommodate, so many things and all you need to concentrate, you have to prepare the mask. The simulation software and all you cannot use it for fabrication, only for verifying the performance only.
Okay, ma'am. Whether the convertibility is easily available, ma'am, regarding from Intel suite to this fab converted form?
Converted form means I can't.
Ma'am, yeah, because
No, you can't convert it. So that's why I'm telling you, you can't convert
okay.
it. For example, if you go for Clevin and LED, means you can't convert. You have to make it. You have to make the what is the diaphragm size, each and everything you should give it.
Okay, ma'am. Sure, ma'am. Sure.
Yeah.
Thank you, ma'am. Thank you.
Okay. Yeah. Participants, you can raise your question.
Good afternoon, ma'am.
Good afternoon.
Ma'am, I'm Salakshi, ma'am. Ma'am,
Okay.
actually, I'm from civil department, ma'am.
Okay.
We are working on soil movements, ma'am. To study soil movements, we are getting sensors only from privates, ma'am. And there are less people working on MEMS sensors.
Yeah.
So is it possible for me who's having civil background to develop my own sensor? Is it possible, ma'am? And how long will it take? And what should I do to just start off with it, ma'am?
Yeah, you can do it. You can do it, but you should. But before proceeding this, first you should clear with your. You should have clear idea. So for what kind of sensors you need? What's just now I have presented. No, so what's your requirement? So how you can use it for your application? Those things and all you should confirm first. Okay, so then according to that only you can design it. But definitely you can do it for your work also.
How long will it generally take, ma'am? Like to
How long?
how long will it take for us to develop a sensor, ma'am? With
Yeah, that
some.
depends on you only. That depends on you only. How can I say? So first you should these initial steps and all getting over only. Then you can first you should verify with the simulation. The simulation is hardly once you're familiar with the simulation, no, it's hardly 1 or 2 weeks. You will be finished.
Thank you so much.
Okay. But I want to convey the information to the participants. Actually, in this structure health monitoring area, no, it's a very it's a growing area. So you can do in structure health monitoring not only for civil structures. Okay, you can monitor you can implement the same kind of sensor for human health monitoring or. Still, suppose if you want to implement for building, so many options are available. Actually, so you have plenty of scopes in structure health monitoring. Okay, so just you refer the material. Somebody is for now. Some of you start with they don't have idea how to proceed the research and in how they can define the problem and all. No, so this will be useful. So you read you concentrate on structure health monitoring. Just you read the papers, then you will get idea about this. Definitely, you can perform well on structure health monitoring because it's a growing field. So you can have plenty of scopes, even the biosensors, biomedical. So like that, you can do it. Actually, one session I have allotted for hands-on training on IntelliSuite software. So while attending that session, definitely you will get a clear idea that Vishal actually has had some question, no? And then you can once you don't miss the section because that section is on 28th like that. So that person will give the hands-on sessions on IntelliSuite software, and they give the trial version for 1 week also. So the participants, I request the participants to utilize that opportunity. Definitely will get some idea. So how you can implement for your application, how you can create the structures, like those things and all. You will be familiar with that. Okay. And console also you can try it. The console one software it's available in net. Trial version is available in net. You can download it and you can do it. Okay, you will get some idea. Any doubts or any queries regarding the faculty development program or just you ask me. So the morning session it's not clear actually. So first just.
Yes, ma'am. Network connectivity is very poor.
Very poor, sir. That's why, sir. So
Yes, ma'am.
first, that's why the morning I'm very much disappointed because
And
I
this is
arranged
a
some
natural
speaker for
problem,
the
not a.
morning session. No, I arranged one of the speaker from Tyagaraja Engineering College. His name is Magendran. Suddenly he got some appointment and the 11:40 only he informed me. So that's why it really was.
Okay, ma'am. Thank you.
So that's why. So don't mistaken me. So. That's why. But next day from next 4 days, no, definitely I will do my level best. Okay, so yeah, dear participants, have you filled that feedback form and attendance and all? What about that? Have you sent or not? because you should the morning session someone informed you, I think so. The Atal portal, what they have insisted is you should maintain 80% attendance and you should attend the test also. At the end of the last day, then you should give the feedback, then only you can download your certificate. So okay, so those things and all you should you should have, because you should attend the whole days. If some of you can miss one or two sessions, that is okay. Okay, so the attendance is very, very important. So just to alert it. Okay, so any doubts? Now you received the attendance for the admin session.
No, ma'am.
It is yet to be posted.
Have you received the link?
It is yet to be posted.
Okay, okay. You post it and we can, if there is no question, then we can wind up. Sam.
Ma'am, will we
Ma'am,
get
there are no sessions, ma'am.
Someone has some questions. Yeah, tell me.
Ma'am, will we get the presentation that you presented today, ma'am?
No, I'm not getting you. What?
They are requesting for the presentations, ma'am.
Presentation slides, huh?
Yes, yes.
Slides. Okay, okay. I will post it at the end of the day. No problem. For all the, I collect all the materials from speakers. Then I will post it on Friday or Saturday. That is no issue.
Ma'am,
There
can
are
you
no
provide
questions.
IntelliShip software link, ma'am?
Link. So link, that IntelliSource software link already, that person sent some license, no?
No, ma'am, no, ma'am.
No, no. That Sridevi, you got the mail, the name Sridevi.
Yes, ma'am, but
Actually, 3 days back.
license is not there, ma'am.
Huh? License is not there. But she asked your system configuration, right?
Yes, ma'am. Google Forms
Yeah,
is
she
filled out
asked me to make.
already.
Actually, one problem is I have alerted that person, 2 sessions I alerted to him. So then only they can easily take the hands-on session. For one session, yesterday, what that person.
Ma'am, can I leave the session?
Huh? What?
Ma'am, can I leave the session right now?
Feedback. Quit the session. You need to quit the session. I'm not getting you.
Ma'am, he went back. You can proceed.
Okay, okay. Okay, Sam, you post that feedback link and attendance.
Yes, ma'am.
Ma'am,
Then,
one small request, ma'am. This is Karthi from Kalasani University.
Okay.
Ma'am, if you could post the PPTs on daily basis, that would be fine, ma'am, so that we can recollect the things, whatever the thing which we learned on that particular day.
Okay, 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 I will do it. Okay, I will do it.
Yes, ma'am. Yes, ma'am.
Okay.
Thank you.
Okay. Actually, 145 participants they have applied. Only the chat box now, only the participants now, the attendees are only 59 only. Out of 149, only 59 only is presented. So how we can give that names? That is impossible. So the participants should attend all the session. 1 or 2 session is okay, but
Ma'am, can we close the session, ma'am?
yeah, we can wind up it. You post that link, sir.
Ma'am, I will forward it.
Okay. Okay, we can wind up the session actually.
Thank you for the wonderful session, ma'am.
Okay. Okay, okay. Thank you all the participants for your patience listening. Thank you, one and all. Okay, thank you.
Hello. Is there any feedback link or we can leave the link?
Sir, it is posted in the chat box, sir.
That is not already responded. It is showing you are already responded, sir.
Just wait, sir. We are checking on it, sir.